Hopefully we're going live. Hopefully we're live. Hopefully we're live. Let me know. Are we live? I think it starts. Oh boy, I have to get used to this new way. So it recorded everything. So have you heard a little talking in the background? Yeah, that was me going, okay, did I press this button? Did I do that? Did I do this? You've got so many buttons to press now that I do it slightly differently. Can you hear me? That's the big question. Yes, audio is okay. Oh my goodness, thank you. All right, let me get my screen set up so that I can actually see myself and be able to do this. Okay, I have to do it slow differently than I used to. I don't have a big like monitor. I just have this teeny little tiny monitor now, so I have to like move everything and overlap my big monitor feed with the chat. So I'll figure out a better way soon. But oh goodness, I'm just happy I have audio. No background. Uh-oh, what is that? Please tell me that you see my charts or a bunch of names behind me. Please, please, please. Everybody says everything's coming through fine. Good. You hear me, you see me, and you see my background. Hopefully. And good. I see Mike Richardson's in the chat. He is a moderator. Please be good to him or he will boot you. He is very good at his job. And thanks, Mike. Everything looks good. Wonderful. And I think Jerry will be joining us later. A few amateur radio operators are not able to be with us today because there's all sorts of stuff going on. But I see all of you. Thank you all for joining. And I do know that we have a bunch of new people. Thanks to the solar polar vortex, thanks to it's the G3 level solar storm that we just recently had. We have a ton of new people with us. So that's wonderful. I just have to let you know that if this is your first time watching a mini course, you will get something out of this, yes. But as you might notice above me, this is part 4 of the ground level effects. So this is an advanced course. And so if you go to the E courses, that's what this is. Actually, you know what? I should probably put that on my title slide so that you all know that you're looking at the E courses when you see this. This is E for Earth. And if you look at the playlist that has the E courses in them, you will see there are 3 others prior to this. And the reason why is because the ground level effects are some of the most intense. And they're also some of the most interesting, right? This is where everything, all of the space weather stuff that we got from the sun, from the first chef, that then hits the near-Earth space, which is our near-Earth space environment and our Earth's magnetic system, that then penetrates into our Earth's magnetic shield and then goes all the way through the magnetosphere, the ionosphere, and then down to the ground. So this is the culmination of everything, and really where, right, the rubber meets the road, I guess, is the adequate, the appropriate analogy, because this is what matters to us mostly, right, for just everyday people, and especially when it comes to the big events, because the big events are the ones that we worry about our power grids, and I will actually talk a bit about that today. I have been talking about it, and I'll kind of review some of that, but not in any depth, any real depth. What I want to be able to get through today, because we have lots of charts here, is some comparisons, right, to kind of give you a feel for what we go through and really where a really massive event is relative to the smaller ones, and kind of what to look out for. Because there's a lot of things. I mean, we have all these indices that we throw about, and it matters. It doesn't just matter where we reach on these indices, what level we reach when it comes to a storm. It also matters how long we stay there, because that is really what is the big indicator. So sometimes we'll spike up to these really high levels and people will be like, oh my gosh, it's Armageddon. No, just because we reach a high level doesn't mean the world is coming to an end. And you'll see that with some of the comparisons that we'll talk about. So hello, everybody. Is Lourdes having trouble? You don't see or hear anything. Yeah, come back in, sweetheart. I'm sorry. I think that has to be her internet. She's been having issues with her internet recently. That really sucks. But hello, everyone. I'm so glad you all could join us. I'm thrilled to see you all. And I have a ton of people to thank. First, I'm going to thank my steering committee who makes all of this. These are the guys that steer the ship. They are the ones that meet with me once a month. Some of them in orange here meet with me oftentimes more than once a month, or even privately, so that we can discuss certain things. A couple of you, like Alicia and Rick and Chris, I have yet to get to you this month, so hang in there, I promise. And then the rest of us, we all meet about once a month and really kind of talk about where this community is going, where they want me to focus my attention, and then when new opportunities arise, really what to do with them, how to handle them. You know, I'll oftentimes preview talks and things and some of the data that I've been working with, like with the geocron and stuff. They've seen that develop, and they've also kind of talked with me about what's important and what's not. And we'll go into even more of that. We go into more of that in the behind the scenes. But they're really wonderful, and they keep my feet on the ground. They make sure that I'm doing things for the community and that I don't go off into the weeds and do things that are maybe fun but not necessarily as important to all of you. So a huge thanks to my steering committee. I love all of you dearly. And then my mini course patrons, if you are a mini course patron and you don't see your name here, that is my fault. I wanted to update them this month and I wasn't able to. So if you are a recent join as a mini course patron, thank you very much, and I promise I will get your names up here. It's just a little bit more challenging. As you can see, there's lots of names. I'm eventually going to have to flip to a new page for you all because it's getting harder and harder to find space on this one page for you. But thank you guys so much. You are the ones who are going to be the ones who are going to decide really where the mini courses are going, because this is the final course in basically the first chef, and now we're in the second chef. This is the final course of the second chef. So really, over the past, since I've been doing these courses, we've really kind of gone phenomenology from sun all the way to mud. And so now, after this course is over, we're going to be able to decide, you know, what do we talk about now? Do you want me to go into examples of historical storms, like some of the big ones? I'll talk a little bit about some of the big ones today. But I could go into a more in-depth study about some of that stuff. I can talk about different spacecraft that have come through the ranks and why space weather forecasting, as hard as it still is, it's easier now than it used to be. I could go into the history of space weather. I've had people ask me about that. I could go into different indices and different data products for those who are, you know, hardcore, you know, trying enthusiasts who really want to be able to understand the types of products that are out there and how they're used. There's all sorts of different things that I could do. And you all are the ones that help me figure that out. So that's going to be coming up. So, you know, think about it as you're chewing on the data, you know, the information from this course. Start thinking about what you want to do in the future, because that's coming up pretty quickly. So I'm so used to teaching my Millersville classes. I was about to say, okay, any questions from last time? Well, I won't do that to you. But what I will do is give you a review of last time, because it's been a while. It was last year that we did our last mini course, and that's partly because we had the holidays, and then partly because I had this, you know, massive allergic reaction, just a horrible allergic reaction that caused my whole face to swell up. I looked like Linda Blair on The Exorcist. It was pretty bad. Anyway, so I had to kind of take a little time off, and then the beginning of this year has just been crazy busy. So we're back. And so what I'm going to do is give a light review, and then I'll probably pause and ask, you know, and give you an opportunity to ask some questions before we jump into some of the new concepts and the comparisons for some of these storms. Okay, so that it gives you a better feel for really what big storms are and what massive storms are and what mild storms are, that kind of thing. And so you can feel better when you kind of navigate the whole YouTube landscape and everybody's talking about kill shots and, oh, look at this storm, it's going to tear us apart. And, you know, you can kind of feel for yourself. And I want to arm you with that information so that you don't feel so, you know, I don't want to say uninformed, but there's just not a lot of people that do this for the public yet that aren't scaremongers, right? There's a lot of people that do space weather for the public, but most of them are just trying to get you to poop your pants. I don't want to do that to you. Space weather isn't that bad. I promise it's not. So, okay. Smash says, the main reason we do space weather is because of the implications of heliophysics on cosmology. That's what you generally ask. Well, cosmology and heliophysics are, they're two different fields that are tangential. But I honestly want to do weather for weather. I want space weather to become part of meteorology. And cosmology has a tendency to make people think of things that will never really impact them. It's beautiful to think of Carl Sagan. I love him. He's my, one of my measuring sticks. I mean, he's an amazing science communicator, or was an amazing science communicator, as well as a physicist. But the stuff that he talked about really was much further out than what I talk about. I'm trying to talk about boots on the ground. So it's a slightly different field, but there's a lot of interconnectivity, that's for sure. Okay. Hi from South Carolina. I'm just taking a look at everybody. EMD is doing a comm exercise simulating hurricane on coast. There you go. On the coast, blackouts in the Columbia area due to problems of the nuclear plant, but radio is still getting through. Wow, not a G5 storm. There you go. See, there's a perfect reason why I want to educate you all on what the ground effects are and give you a feel for being able to understand space weather, even if there's not somebody out there like me talking about it directly. You can actually go and understand really where we are, like what kind of impacts we're expecting. And hopefully you'll leave this course with a better feel for really the kinds of impacts that we have on the ground, the kinds of things that you end up seeing, and really how bad things get when there's a big storm, how bad things can get, but also when there's not quite so big a storm, that things can get bad, but we can ride it out. Right, and I want to give you the sense that we can mitigate through these things, because we're much better than we used to be historically, and I think historically is where all of the fear mongering comes from. But we are in a much better place. So, okay, guys. So let's recall, because what we're going to do is obviously if we're going to be talking about boots on the ground, what we need to talk about first is remind ourselves about things called L shells. Now, if you remember from the M courses, this is really when I first started getting into L shells. L shells are really a way that scientists talk about what's going on in the Earth's magnetic system. And the reason why, and where's my slinky? There's my slinky. Hold on, let me get my slinky. You guys know me and my slinky. Oh, goodness. Where would I ever be without my slinky? You guys all know, hopefully, if you've seen the M courses, you all know that the Earth's magnetic system is kind of like, at least the heart of the Earth's magnetic system is kind of like a slinky. If you have Earth kind of sitting in the middle, then this is like a toroid, right, that the Earth kind of sits in here. And so if I put it, like this, and tilt it the right way, oops, tilt it this way, you kind of see, tilt a little more, you can kind of see, you see how the shape behind me? Do you see how that kind of fits, right? You're seeing the field lines coming out like this, right? So that's what you're looking at when you're looking at these field lines, okay? You're looking at nested shells, in a sense, nested slinkies, one inside another, inside another, inside another. And these shells are really, oops, let me put this over here. These shells are really what they're important, not just because they they order everything that goes on in near Earth space. They're like they jail particles, for example, because remember, everything in space is charged. So with all the particles being charged, then they're going to see electric and magnetic fields. And as they see electric and magnetic fields, they're going to have to obey. We call it frozen in flux. And what happens is that particles then will see these fields and they will move accordingly. And if they're jailed on a particular, what we call field line, then they're going to stay on the slinky that's defined by that field line. They're going to kind of move around. They're going to what we call gyrate. They're going to bounce back and forth, and they're going to drift along that field line and kind of smear themselves out along that particular slinky. Okay, so these are nested slinkies that come out. And even though you're only seeing them as a single line in this two-dimensional picture, they're really shells, okay, that go all the way around. So we call them L shells. They're measured, if you all recall, they're measured by the equatorial, right, the equator, the magnetic equator, which is tilted relative to the geographic equator. Here's the pole, and the magnetic pole and the geographic pole. So the geographic equator is, where is it, like this, kind of tilted, a little bit down, whereas the magnetic equator is tilted this way, okay? So they're off by an angle of about 11 degrees, okay? Because if the poles are off, then the equators are also off because they're perpendicular to each other, right? So you measure an L shell by the magnetic equator, and the reason for that is because that's the furthest out that an L shell, one of those slinkies, gets from the surface of the Earth, or from the core, if you really care. So it's the furthest out, and we measure them in Earth radii. So if this is what we would call L1, right, because it's 1 Earth radius from the center. Out here would be L2. So this is L1 and a half. This is L2 because it's now 2 Earth radii. This out here is L3 because this is now 1, 2, 3 Earth radii, and so on, and so on, and so on, okay? Notice as the L shell goes up, higher L's, further out, okay? Geosynchronous orbit is at an L 6.6, okay? So about 6.5 Earth radii out, which is beyond what you see on this page. But and geosynchronous orbit is on the hairy outer edge of the Earth's outer radiation belt, okay, just inside that. So from L of about 4-ish to about 6.5-ish is the outer, what we call the outer zone. That's the Earth's, the outer radiation belt. The inner radiation belt is sitting around L of 2-ish. Comes in a little bit. It's kind of fuzzy because the particles have a spread of energies. The spread of energies get trapped in different L shells, okay? So it's kind of smeary, right? But what's important about this is that if you trap these different particles and these different distributions in these L shells, then they will move in and around these field lines. And if they dip down and precipitate in these areas, you're going to have effects that are linked by latitude. Because if you notice, low L shells are at lower latitudes, where they dip in and touch the Earth's surface. Higher L's go in at high latitudes. See the difference? So there's a latitude dependence that you can map literally to the ground. And that works for both particles that are precipitating, what we call precipitating, basically flying in. But it also works for wiggles, because remember, the Earth's magnetic shield is very springy. And if you recall from the M classes, when you have a big geomagnetic storm, a big solar storm hitting Earth, a big CME hitting Earth, okay, that the impact of that does all sorts of things, right? The actual the worst part of that impact actually oftentimes is from the tail, because it peels back certain parts of this magnetic shield, peels parts of that back, and it stretches out the tail and makes it like a slingshot, and the tail gets so unstable that bing, it reconnects and comes back forward and slams particles in through the night side of Earth. Now, if all of this sounds kind of weird and wild, check out my M courses. You will absolutely see that, because we talk about how a geomagnetic storm occurs. Most people think coronal mass ejection, when it hits Earth, it's going to impact from the front, or it's going to impact through the poles. Untrue. It actually impacts from the night side. Okay, you do get a bit of a push, like a bumper car boing kind of thing from the front, and we'll talk a little bit about that because we can see the effects on the ground. But the biggest effects actually occur on Earth's night side. And it's just the way the Earth's magnetic shield works. So it's non-intuitive. Well, but then again, so are all these L shells, I'm sure, right? People don't necessarily like L shells because they're not easy to kind of visualize, right? Because all of these lines, of course, are invisible. They're just magnetic fields. But magnetic fields and electric fields, right, they govern all of the dynamics inside this system. So it becomes a very beautiful ballet of sorts. At any rate, what's cool is that you can map all of this craziness on the ground just by looking at the latitude of which you're seeing disturbances, okay? And again, higher latitudes map out to higher L shells, which means further out in the Earth's magnetic shield. And that has huge implications when it comes to effects on the ground. Because obviously, if you're further out in the Earth's magnetic system, you're going to have bigger impacts early on, because the way a big solar storm hits, it's going to hit from the outside in, right? It's going to work its way in, right? So the outer stuff gets hit first. That's why aurora happens both in the north and the south, up high, and then it works its way down to lower latitudes. And then as it goes away, it retreats back up to high latitudes. It's because you've got a system that's working its out way in and then back in way out as everything begins to heal. Okay. Again, that's all covered in the M classes. And if you want to know more about aurora, of course, then you go, I think, what's the next one? Do I have it for ionosphere? I forget what the name of that next classes are. But then you go to the ionosphere after the M classes. At any rate, so really what I'm doing here is I'm just showing you a map. So here are the L shells again, okay? Slightly different way. You can see the latitudes get higher as you go higher in L shell, right? So you've got L of 5, which maps clear up here, but L of 1.5 maps down here. And you can actually see that on this map, right? Here's L of 1.5, and it dips, right? It's not the geographic equator, it's a magnetic equator. So what ends up happening is that you see a bit of a dip because it's tilted relative to the Earth's geographic equator. Okay, so that's how it maps onto a projection like this. But notice that as you go higher in latitude, right, and you call this, and you can call these magnetic latitudes. You can, obviously there's a mapping that goes from geographic latitude to magnetic latitude, but same kind of idea. L shells, as you go higher in L shell, you go higher in latitude. Right? So geosynchronous out here, way out here, is clear up in high, you're in the high part of, you're in Canada. You're in, Alaska. You're in the Northwest Territories and stuff. And way up in Norway. Really the high areas, right? And the same happens for the southern hemisphere, right? It's just reversed. So L of 1.5, right, is close to the equator, and then it goes up, 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 up to higher latitudes in the south. Okay, so that's how it maps. But the neat thing is if you have magnetometer chains, and this is what we've been talking about as we started the ground, the Earth-based courses. If you have magnetometer chains all through this area, well, depending upon where the magnetometers are, tells you what L shell, tells you, my goodness, tells you what part of the Earth's magnetic shield is being affected, right? And how deeply penetrating some disturbance is. And for those who've taken all the courses, you know that it has to do with current systems, right? And again, this is just review. I am not going into this in depth. So for instance, KP, which is a beloved global index, right? It's magnetometer based, right? These are magnetometer indices. There's like 12 of them. And you can see some in the southern hemisphere and a bunch in the northern hemisphere. It's because there's a lot more land in the northern hemisphere than there is in the southern hemisphere. This is mostly ocean. So it's harder to get mid-latitude observatories. In this case, we're talking about mid-latitudes. And the reason for that is because we're trying to capture in the KP, right? The K index, the P in K is planetary. What we're trying to capture in this index, pardon my dog, what we're trying to capture in this index is a little bit of what's going on at really, really high L's, high latitudes, and what's going on kind of a little bit further, a little bit closer to the equator. And if you look at current systems, and you've got a couple mapped in here. Now, I'll take the moment to orient you in this diagram. Sometimes I forget to do that because I've seen it so many times that I'm just like, oh yeah, everybody knows what this is. And people go, what the hell is this? Okay, remember the slinky? Remember the heart of the Earth's magnetic system, right? I wish I had I do, hang on. Oh, pardon me, we've got visitors, so I apologize. Earth, not really blue, but if you're colorblind, maybe you won't know. It's a very dark red ball. But if I put that here, see, I'm trying to kind of give you the idea. Okay, so Earth sits kind of in the middle of this, right? It's not a perfect example because if it were really perfect, the slinky would go inside of Earth to the Earth's core instead of just being hanging out on top. Excuse me, I've got a nose, my nose is running. I have no idea why. Okay, but this, okay, and if I move it and put it in the right place, is really here. Let me pull it back a little. tilt it quite, kind of like that. Okay, so here we are, the Earth with the little slinky and the heart. It sits right about here. Okay, now I'm going to pull this away. Everybody got this image in their mind? Okay, I'm going to pull it away. There's Earth right here. Okay, and then this is part of that slinky. That's part of one of those L shells. Okay, no, there it is again. See? And all that, the stippled part, that's all this inner magnetosphere, heart of the Earth's inner magnetic system. Okay? Now, what they've done in this diagram is they've taken a vertical cut right through the Earth's north pole to the equator. And then they turned their knife sideways and went and sliced out that way. Okay, so they took a big, nice cake slice, turned sideways and sliced out that way. Okay? What this whole cavity is the entirety of the Earth's magnetic system. And so in the front, you got solar wind coming this way, and I'm sorry, my image, I probably should, well, I can't do that now. This says solar wind, but I have this thing blocking it. I'll put this down. Okay, so solar wind comes in this way. You've got this up front, right? This is the front end of the Earth's magnetic system. And then the back of it is stretched out in a big comet tail, big long cavity. And we're not going to go into the magnetospheric dynamics, why it does that. That was all the M courses. But what's important here is that we're talking about current systems, and that's what's colored in, okay? So you can see there are these current systems that come into the high latitudes, right? High L shells. Well, look where they map. They map clear out to the edge. High L shells, right? You go further out in the Earth's magnetic system, you're getting higher and higher L shells. You get to the edge of the magnetic system, that's the highest L shell we got. Well, that's what we get. In fact, region 1 currents are the highest. They're either right at what we call the magnetopause, which is the edge of the Earth's magnetic system, or just barely inside it. People still argue about that sometimes. So that's region 1 and region 2. Yes, they are associated with aurora, right? And they're the ones that light up first. They're the ones that get energized first. Where do they dump their stuff? High latitudes. Why? High L shell. And what do? They make that magnetic field go, right? Or the magnetic field goes like that, and it helps energize these, okay? Because we're getting a big solar storm, a big CME injection, or some fast solar wind, or something like this, and we're getting magnetic field and density and particles being flooded into this system. And if it's got the right configuration, it can unlock this door, in a sense, here in the front, peel back some of this magnetic flux, and inject all of its particles, and then they get shot this way. And it also energizes all of this outer layer. Okay, so you get particles that are being shot in here. Right? And again, this is an L shell, so it goes all the way around. Got it? So when we map all this out here to this edge, it doesn't just mean, oh, this current system only lives here. No, it lives all the way around. That's why aurora is like a cap. It goes all the way around. Right? So that's what we're dealing with when we deal with solar storms hitting. And if you go just inside of that to a little bit deeper part, you get what's called the ring current. That's in purple here. Okay, that's further in. Well, that means lower L shell. Well, what does lower L shell mean? Lower latitude. So now we're talking about down in here. Okay, so as we get down in here, the ring current, there's actually a different index, and I talked about this last time, called DST, that isolates this current system. Because you can think that if you have different magnetometer chains at different latitudes, you might be able to isolate these different current systems and know just what's going on at the outer edge, just what's going on in the ring current, just know what's going on deep inside, just know what's going on right out in the front where some of these other currents exist. Okay? That's the whole point of having magnetometer chains everywhere. Is they're a proxy, they're a way to probe the Earth's magnetic system everywhere without actually having spacecraft out there. Now, do they tell you everything? No, of course not. But they're a better sounder than nothing. I mean, we don't have constellations of spacecraft swirling all around the Earth's magnetic system. That would be way too expensive and hard and, I mean, people go, why are you spending that much money? You've got magnetometers. We can't even keep the magnetometers funded, okay? Try to imagine having a huge constellation of spacecraft being funded by NASA or something. People would be in an uproar, going, why are you doing this? So we basically settle with magnetometers to a great degree, okay, unless we're doing science. But for operations, magnetometers are really where it's at. And in KP, we actually have magnetometers that kind of bridge the gap between the lower latitudes and the higher latitudes. So we're kind of sampling all of it. That's why KP is so cool. And why people use it so much is because it gives you a global feel. Not only are they at all local times across the globe, you've got some in the southern hemisphere, some in the northern hemisphere, but they're also at multiple L shells. They spread a lot of L shells so that they get a little bit of something from the auroral electrojets, which is really what you're seeing out when you come way out here, and they get a little bit of something from the ring current, okay, which is different than, let's say, DST. If some of you actually know what DST is, if you've watched my previous courses, you'll know, right? One of the, I forget which E course it was, but we went into that. We went in what's AE, the AE index, what's it used for, DST, what's DST used for, what's KP used for. And so I'm just bringing up KP because that's the one that everybody always seems to default to. Oh, KP, it's one of the longest living indices and most well known. And so everybody says, oh, well, this is the index. Well, it is for certain things, but not for everything. And the savvy person knows what to use KP for and when to abandon it, because it may not be giving them the information they want. But this is how scientists on the ground manage to try to make sense of all of this dynamics. Okay. And it's a very powerful tool. And there's lots of different types of indices that we use for all sorts of things. And Potsdam, GFC Potsdam, is a great place to go for that. Oh my goodness, they've got so much history. And I did talk about that. As a matter of fact, that's where these plots come from, by the way, which I don't have. I apologize for not having them labeled, but excuse me, it's coming from there, but that's where they come from. And my previous courses go into that and show all of that for lots of different indices. And there's just so much information there. It's not even funny. Makes my head spin. Okay, so hopefully, let me see where I am in the review. How much review? Oh yeah, I've got a lot. Okay, I'm going to jump into geomagnetically induced currents here. And I guess I could pause here for a second to see if anybody has any like intense questions, anything unclear about this, because the point is, when you have stuff like this, right, and you have magnetometers, you're obviously wiggling magnetic fields a lot, because magnetometers, that's what they read. When you wiggle magnetic fields, you create electric fields. Okay, so a time-varying magnetic field creates electric fields. When you create electric fields, now if you have anything that's polar, that can be polarized, like metal, like rock with metal in it, like earth, right, like the stuff we stand on, then you can actually cause potentials to be induced in that rock. And you can also drive currents. Okay, and so that's where we get into geomagnetically induced currents, is when you make the Earth's magnetic field rock and roll during a big solar storm, well, it's going to induce currents in the bedrock. And rock doesn't like to, it doesn't move currents very well. So the currents try to find other places to go, like power lines, which we'll talk about in a sec. So is anyone confused by this? Hopefully everything's cool, right? And I don't want a bunch of questions that are like left field. Don't ask me about, Betelgeuse or something like that. I don't want to hear about that stuff right now. I just want to know if anyone is totally like lost when it comes to L shells and what I'm trying to talk about here, at least in a general sense. Yeah, TEC are different. You don't need magnetometers, and TEC are, total electron content. That's up in the atmosphere. And they will not be directly correlated. It's very, very different. Yes, obviously there's similarities when it comes to having a geomagnetic storm and then having the TEC change. Yes, but it's a different mechanism by which it happens. One is more magnetic fields, that's down at the ground. The atmosphere is more about particles and particle precipitation and heating. So that's a bit different, which I go into in the ionosphere set of courses. Tamitha, can you tell or explain, this is Ricard, can you tell or explain on what scale to which extent the geomagnetically induced currents? Oh, yes, we're talking volts, and we will get there. So that's good. You're asking questions that we'll be getting to, yes. No, don't worry about your English. I can read through a lot. You know, and if I don't understand your question, I will ask you to rephrase. I understand completely that some people here, their English is not their first language, and I appreciate you trying to learn in English. It's very kind of you. I'm honored that you're here. A differently charged object breaching double layers at speed. Oh, you guys are having a conversation with each other. I love it. Okay. Good, Ankit. I'm so glad you're going to become an English teacher. All right, so, okay, it looks like everybody's good. I don't see any questions other than that one question, which we will get to, P. Ricard. We will get to the whole concept of volts and stuff like that, because I'm going to do a comparison of different storms, and we'll see. And you'll actually see a data product from the Space Weather Prediction Center, at least for the United States, that they're going to extend into Canada here very soon. I've already seen work that's being done on that behind the scenes that they've presented at scientific conferences, which is really cool. In fact, in April, I'm going to go to the Space Weather Workshop and hopefully see a lot more of that. But if doing these types of geological surveys that the USGS does and that Space Weather Prediction Center does, if it ends up being really useful to these power grids and these power grid consortiums, I'm hoping that we're going to start seeing some of that being done in other countries as well, you know, in the UK and in Europe, and then of course down in Australia. Actually, he's an ionospheric physicist, but I should ping Brett Carter about that to see if they've got people working on something like that, because Australia really needs it as well. Okay. What specifically in the solar wind impacts the L shells? You mentioned CME. What is in the CME that causes the L shells to be impacted? Magnetic field mainly. That's the number one thing. But it is also particles. There's density. There's energetic, or not energetic particles, just plasma. And those together conspire to create a geomagnetic storm. Now, if the CME doesn't have magnetic field configured the right way, so like take two fridge magnets, right? There's two different conditions you can have. You can have the two fridge magnets have the polarities pointing the same direction, and you put them together and they repel each other. You can feel it. You can feel the magnetic forces repelling each other. In that case, if that's the Earth's magnetic shield is one of those magnets and the CME is the other magnet, they will become bumper cars. So the CME will literally bounce off, in a sense, and blow over the Earth's magnetic system and not couple into it. But just like the fridge magnets, if you reverse one and you feel them attract, they click together. And what happens is that you get this reconfiguration so that the two separate magnetic systems reconfigure to become one magnetic system. And as that happens, then that CME is able to pump all of its junk in there. So all of the stuff, all of the force, all of the energy goes into the Earth's magnetic system, and there's a lot of there's a lot of dynamics that occur. And that's when I talk about the slingshot. That's when I talk about plasmoids going down the tail and Earth particles being shot earthward. That's when aurora becomes much brighter, and also the auroral oval grows, because we call the ionosphere, the upper atmosphere, the exhaust pipe of the Earth's magnetic system. It basically gets pumped full of all this stuff and it doesn't know what to do with it. So it pumps it into the Earth's upper atmosphere and dissipates it. But that dissipation causes not just aurora, but heating as well, because it's putting currents in the upper atmosphere. It lights up the upper atmosphere like a big neon beer sign. So it's really cool. And the dynamics of all of that I talk about both in the M courses and then in the, I believe it's the I courses, right? The ionospheric courses. And if you want me to, after we're done with all this, I can go back and show you a little bit of that at the end and kind of walk through some of that. If you are on Patreon, also, I believe I have it on my website now open to everybody. You can look on my website, and also if you're a Patreon member, you can look and see the course curriculum and get a walkthrough. I actually have a video where I walk through what the courses are, how to take them, and that kind of thing. Because there's like 28 courses that we've done now. It blows my mind we've done so many. But we've done them all on these topics, both the solar phenomena and then everything in the Earth's magnetic system. So you can get literally a training all the way from sun to mud, because this is the last of those courses. So hopefully that answered that question. But I don't see any of us talking about, let's see, lots of magnetic L shells, odds and evens, how and where they connect at Earth, come to mind. Okay, but you get it roughly. Oh, good, 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 good. Thank you, Metal Halo. I appreciate that so much. Can I point you to a good study of CME flare storm correlation severity of global earthquakes? No, there aren't any yet. And the reason for that is because mainstream science, mainstream space weather physicists are not going to touch that because the geophysicists haven't been able to back out the primary drivers, the geological drivers of earthquakes yet, well enough for mainstream space weather physicists to be able to get any funding to even go there. There's the uncertainty in doing those types of studies is so broad that we couldn't, as space weather physicists, the effects are secondary, possibly tertiary effects. And so there's not a paper that could be reviewed, peer reviewed in such a fashion that it wouldn't be rejected. And until there's some type of arguable something in fringe science that could pass peer review, like really pass peer review, you're not going to see a lot of NSF or NASA funding. And sorry, that's how mainstream scientists live. They don't do this stuff, you know, they don't have the ability to do this stuff for free. So they have to get funded. And if we can't convince the funding agencies to fund those types of disciplines because it's too far out yet, too far advanced, and some of the other science in the other fields like geophysics hasn't caught up with it yet, you know, we just have to wait. So I don't think you're going to find many, if any, peer-reviewed papers. But you know, the neat thing is that we are beginning to see peer-reviewed papers with, you know, passing MOXIE in at least coupling ionospheric, you know, weather with and neutral atmosphere weather with space weather. So like different things with big storms, hurricanes, and things like that. We're beginning to see some of that, which is really cool. And I'm hoping that we'll see more of it because that's one area where we're seeing that transition from fringe to mainstream, and I love it because there's really connectivity. We know there's connectivity. It's just really hard to find right now because a lot of the other sciences have not been able to get through it yet. But anyway, I digress. I apologize. Okay, so let's talk about GICs. Okay. All right. Again, this is still review, but I'm going to go over this reasonably quickly. Notice this is all they have. This is the problem with doing with having so many disciplines be having to cross so many different disciplines in order to understand something from sun to mud. People who understand GICs really well look at a CME and basically are able to take a CME and just turn it into like 3 different lines that are just impacting the upper atmosphere. It's like, this is not what a CME looks like, nor is this the only effect a CME has. But this is their cartoony interpretation of a coronal mass ejection. Don't believe anything you read up here because it's all kind of, you know, beyond simplified. It's just some of it's wrong. But what matters is when we start talking about what happens down here, because this is a nice gentle cartoon that gives you an idea, right? You've got different parts of a power grid. Right? You've got the generation structures where you actually have the power generation being made, and transformers then have to that are anchored into the ground have to step up the voltage. And the reason for that is because it makes it easier to with lower loss when you step up the voltage. So then they can go across a huge set of mileage. Right? This is the transmission lines. So these are the big intercontinental transmission lines that have these massive towers, right? This is where we have problems with GICs, okay? It's because you have hundreds of miles, hopefully not anymore necessarily of unbroken lines, but we used to, especially when we had telegraphs, we used to have hundreds and hundreds of miles of unbroken lines. And that's where GICs become a problem, and we'll talk about that in a sec. But notice if once you've done this at high voltage, you stepped it up, then you go to another transformer, once again buried into the ground or anchored into the ground, that steps down the voltage, so then you can go into your distribution, right? So this is now lower voltages where you can actually go, you know, different voltages for residential, different voltages for commercial and industrial, but you have these other, you know, substations and power things that just distribute this power back out. But in this transmission section is where you have problems. And anytime you have anything anchored deep into the ground, like you do with these step up and step down transformers, that's where the problem is, okay? Now, understand that these transmission lines really aren't the problem. It's really the fact that they stand over such a massive distance. Because the Earth's magnetic field, remember this, the Earth's magnetic field is only as strong as a fridge magnet. It really is. The problem is it's a fridge magnet the size of Earth, okay? So when you have long transmission lines, big structures that span hundreds and hundreds of miles, a tiny bit of current that the Earth's magnetic field wiggling can induce, that's not a big deal if it's over a short distance. But you keep adding up that distance, you add up the little incremental currents, and it becomes bigger and bigger and bigger until the point where it's like massive. So you can get a huge potential drop, right? And therefore big currents driven. If you've traveled, huge places, long distances. This is why when people say, oh, a big solar storm is hitting and the the GICs are going to blow my pacemaker, they're going to blow my car battery, or they're going to destroy my cell phone, it's going to explode, because you see these things in in how many movies, right? Where you even see it in documentaries anymore. People's computers explode, or people's toasters catch on fire, and it's just like, oh, good Lord, please help me. And car batteries are going to die, because you've seen experts, supposed experts, talk about this. No, that is not what happens. If your car battery was the size of Lake Michigan, okay, maybe, right? If you had a pacemaker the size of, Fort Knox, okay, maybe, right? Not even Fort Knox, it'd have to be the size of Wyoming. I mean, we're talking about massively large things that go over hundreds of miles, not teeny tiny electronics, right? The Earth's magnetic field is the strength of a fridge magnet. What's it going to do? You put a fridge magnet next to your pacemaker, you think you're going to have a problem, right? You're going to put it next to your computer and your computer's going to explode? Come on. So that's where the one of the big scaremongering aspects of space weather comes from, is that people don't understand that, yes, big things can happen, but it has to happen to big things, okay? Because what ends up happening is that if you have a ton of bedrock down here that has metal, or it's got some kind of ability to conduct electricity, well, you're going to induce currents, you're going to induce potential, you're going to induce currents. Currents are going to flow, but they're flowing in rock. They don't want to flow in rock. That's highly resistive compared to transmission lines. So electricity will always find the path of least resistance. And if it finds one of these guys that's embedded, grounded here, and it sees it can go from here to here because the Earth's magnetic field is telling it should, right? It's being forced to flow because the Earth's magnetic field is creating these currents. Well, it's going to want to flow through this, but it can't very easily. But it sees, oh, I could flow through this. So pop, it jumps up into the transformers and flows really smoothly and gets back down to where it's supposed to be, right? So now it short-circuited, right? All through this. It didn't have to go through this. It could pop up in here. Well, that's great. That's wonderful. It's what we call free energy. Hey, you want to go green? Just get us a geomagnetic storm. You get free energy coming from the rock itself. Problem is, this kind of free energy isn't something we were looking for. Our transformers don't know how to deal with this. It's too much, too fast, wrong frequency, wrong everything. And we'll talk a little bit more about that. Okay. So a quick summary of what happens with GIC effects, right? You get the electrical grid providing an alternate current path. It doesn't have to go through the ground. Okay. And so these essentially DC, not alternating current, because there's not periodicity necessarily. Yeah, you get a lot of wiggling, but it's really short-term, just direct current, just straight, pulses being fed into the transmission lines. And remember this too: it's the GICs, right? These are not ground-induced currents from that sense. Geomagnetically induced currents. These currents are not induced directly into the lines, okay? It's in the rock. Whoop. And then they couple up into the lines. Yeah, the greatest, the biggest induced currents are in the highest voltage transmission lines. Again, it's the length of the lines that makes the big difference. The distribution lines that come down are the lines that step up to get to the transmission. The big high voltage transmission lines, those are short. But the transmission lines that's the long leg. Okay, so that's why they're so much more vulnerable. Obviously, it's going to be dependent upon geography and geology. Why? Geography, because of those L shells, right? The higher the L shell, right? The higher the latitude, the more the magnetic field is wiggling during a big geomagnetic storm because it's closer to the front lines, right? I don't mean the front lines like transmission lines. I mean the front lines of the space weather event that's hitting Earth's magnetic shield, right? We remember? Higher latitudes, more wiggle, right? Higher latitudes, further out because higher L shell. Higher latitudes, higher L shell, further out, more wiggle. I'm sorry, am I being goofy? I apologize. So that's how it depends upon geography. Geology, it depends because what kind of rock are you sitting over? Are you sitting over rock that's going to, that has a lot of, ability to conduct electricity? Can you get a big potential in it? And so that will dictate what, if you've got transformers that are buried in that rock, then those lines will be more susceptible because bigger currents can flow, right? So it depends both on geography, where you are, and geology, what kind of rock you're sitting in. Okay. Obviously, it's dependent upon storm intensity and orientation. I'm not going to go into I think I have a couple slides I'm talking about the saturation of transformers. I'm not going to go into that nearly as intensely as I did last time. That doesn't cause an increased reactive power demand. I will remind you of that because a lot of people, to me, that's one of the most important aspects that's, once again, non-intuitive. Most people don't understand. They're like, oh, well, just take the grid offline. Oh, no. That is the worst thing to do. As a matter of fact, that's why the 1989 Quebec event, why it was such a catastrophic event, is because the power grid folks back then didn't realize you can't take these these power these systems offline, these substations and these transformers and these sectors offline. But all their fail safes, all their protective relay equipment took them offline automatically because they didn't understand what was happening. And that's just the way you do it. You just, when something is being overloaded, ooh, something's wrong, take it offline. Right, but that actually caused or at least really contributed to the grid collapse because it took out reactive power. Okay, we'll talk about why that is. Yeah, and we'll talk about, I'll go into that here, but it's all about increasing the reactive power demand, and I'll talk a little bit about how it's kind of, you can almost look at it like a spring system, and I'll mention that when I get to the slide. But you've got heating, you create harmonic currents, and you can create voltage collapse because you basically reduce the amount of actual power you can deliver. Because reactive power comes at a cost of the amount of power that you're able actually to deliver out to the grid. And the grid will collapse if you demand too much reactive power. You can basically take up the entire grid with reactive power by forcing it to kind of store power, and then it's not able to deliver. And I'll talk about that more in a sec. Yeah, we also will talk, I'll mention to remind you, we talked very much intensely, we talked very much last time about how you can actually look at the oil that's inside, that's used to cool the transformers. You can actually look at that oil and tell by what gases and what things are being liberated in that oil, what temperature it is and how close it is to breakdown. It's very interesting. This is a reasonably new methodology of checking, kind of in a sense, the health and safety of these transformers during a geomagnetic storm. It's really kind of cool. I'm hoping that we do this more and more. Obviously, you can get damages to winding. We talked a lot about that. And one thing I mentioned, and I didn't talk too much about it, but I have gotten this confirmed, that next generation power systems, they do have more relays. So the wind and the solar as we keep hooking in these new generation, these next generation power, these green energy power sources to our grids, sadly, they have more relays. And these relays actually are far more susceptible. So we think, at least perfunctory understanding of these next gen power systems, is that it could make us even more susceptible to geomagnetic storms. So I'm hoping that there's going to be enough awareness soon that we're going to start factoring in more of that. Oh, are these space weather ready? Because that's never been a question that people have asked, right? So, and any combination of all of this stuff can lead to cascading failures. It's a very complicated problem. Okay, so yeah, it's a multifaceted problem. So the issue with transformers, when we talk about it, it's really the transformer heating that we worry about. And I think I know I talked about it before. Part of the issue that you have, hold on. Let me check to see, do I talk? Maybe I don't. I'll mention it here just because I don't think I saw it anywhere else. I may have taken out the slide that talks about this. Part of the issue that we have with transformers is that if the transformer is new and is a dry transformer, it can handle heating pretty well. It's quite robust to a lot of different aspects of GICs. But if a transformer is wet, which is an old transformer, and water has managed to leak, because remember, a lot of these transformers are obviously they're outside, right? So they have to deal with the elements. And condensation's a big deal. And so when transformers get old, some of the gaskets, some of the things that protect them from the outside elements, doesn't cause them to have problems functioning under normal circumstances, but it can make them more susceptible to space weather because you can get water inside the oil. Now, this is oil is the cooling oil, okay, right? You can't use necessarily, antifreeze or something, but it's kind of like the same idea that oil doesn't boil at low temperatures, it boils at very high temperatures. And so you can continue using it as a viable coolant for a very long time. The problem is, over a vast number of temperatures, very high temperatures. The problem is when you get water in that oil, obviously water boils at a much lower temperature than oil does. And the water, because it doesn't mix with oil, it ends up settling on the paper insulation of these transformers. And when a transformer gets stressed by these GICs, which we'll talk about in a second, the problem that you have is that the water will then boil. It will cause the oil to heat. And as soon as it heats above 100 degrees Celsius, well, that water boils out of the paper. In the process of boiling out of the paper insulation that separates the transformer windings from one another, in the process of doing that, it shreds the paper. So now you've lost your paper insulation between these windings, and the windings are much easier to arc and spark. And so that can be a real problem. And obviously, if you're going to arc and spark in oil, well, you got a bomb, right? So there's a huge difference between wet transformers and dry transformers. And that, sadly, for the really big storms is not I don't think that's well characterized. And I think that there are some people I've met in the power industry that's what keeps them up at night. My friend, Mr. Fenton, is one of those. He gave me a really good training in that. So I've talked about that before, and I will not let that go because I just don't see that discussed enough. At any rate, GICs. So when you talk about GICs in terms of current, this is just a thing, not showing voltage necessarily, but current. Current in an alternating circuit goes up and down, right? You've got, here's the zero level, and basically you're just alternating the current from positive to negative, okay? So positive current, negative current, right? And you've got a periodic function. And this is a frequency, for those of you who are used to seeing this, because this is going over time, right? We're not talking about seconds here, but we're obviously you have 60 cycles per second, so this is, not even a full second, not even close, right? But when you have so this gives you a frequency, and the transformers are tuned to this particular frequency. It likes this frequency, it knows it, and the transformers are made such that they don't that they have optimal operating capability with a particular frequency. Obviously, in the United States, that frequency is going to be 60 hertz. And I believe they don't I don't think they transform anybody might know the difference if they transform the frequency of the power, the amperage. I think it stays at 60 hertz even in these big transformers. I don't think they step up the voltage, but I don't think they change the frequency of the wavelength here. I don't think they alter that. If anybody knows better, let me know, because I might be speaking out of turn. But when you have those currents that are induced in the rock, okay, when you have them induced in the rock and then they come up through these transformers, through the ground leg of the transformer to be able to go into these transmission lines, what happens is it's free energy. Okay, it's free current, right? A lot of free current, and it's DC. So basically, you get these add-on, these bump-ons. Okay, the problem with that, and it depends, and you can see, depending upon how much, how strong the GIC is, you're going to have different levels of these bump-on, these adding on the peak. You're also going to shift that peak. Okay, so now you're causing problems that is in a sense a harmonic, what we call a harmonic distortion, because it's a different frequency. This peak is thinner than this one, so it's a different frequency and it's shifted. Its phase is shifted. And so it causes us distortion. This is where the heating comes in, because now the transformer's not ready for this. It's not designed to do this. But look, it's free energy. Wouldn't that be great? Someone I know, someone close to me, I know, said, wouldn't it be cool if we learned how to capture that we could actually use the free energy that we're getting from the Earth during these GICs and store it somewhere? I thought, wow, that's kind of a neat kind of way of thinking about green energy, but I'd never really thought of it. But yeah, wouldn't that be nice? So it's wonderful in the sense that we're getting all this extra current, but the problem is the transformers don't know what to do with it and can't store it. Plus, it's not the right frequency, it's not the right phase, it's shifting the peak, and it's heating. It's heating lots of things, okay? This is oftentimes in a normal circuit. If the protective relays saw this in a normal operating situation, it would go, holy crap, something's wrong, shut it down, right? Totally take that transformer offline because it knows it's seeing distortion that shouldn't be there. Therefore, something's feeding into it, something broke, right? Which is fine if it's a normal operating environment, because this would likely be the only transformer that's seeing this. Okay, so the protective relays would shut it, remove it from the grid, and everything would be great. The problem is, during a geomagnetic storm, they're all seeing this. And so when you try to start pulling down a bunch of them, especially at high latitudes, because they're going to see it first, well, now you're putting a much bigger load on other transformers that are still in the circuit, right? So the first thing you do during a geomagnetic storm, if it's strong enough, is they take this protective relay, they take their normal operating procedures out. They say, no, leave it on. I know we're seeing this, we just have to ride through it. They don't take out these, they don't remove these systems. They make them live through this, okay? But it's important, and we'll talk about why in a sec. Now, I went through this in great detail, the power factor. This is, and I'm not going to go through it nearly to the level that I did before, because it's not, you can go back and look at the previous course, E3, and see more detail. But I'm just reminding you what the power triangle is, okay? In a circuit, this is really simplified, but in what we call an RCL circuit, in a power grid, in a sense, you have transformers, which are like load-bearing resistors. You can call them resistors, but you also have capacitors, which store energy, and I won't talk about how, but you also have inductors, which store energy. Capacitors store energy using charge. Inductors store energy using magnetic fields, okay? So in what we call an RCL circuit, you have both ways to deliver power, right, through a resistor, and you have ways of storing power by charge collection and by magnetic field collection, in a sense. Okay. So you can start, so what that allows you to do is it allows you both to deliver and store. Now, what is a really good analogy that I came up with just recently, so I'm glad I'm able to share it with you now. if you think of an analogous kind of thing, oh my God, I can't believe this thing's going to come in handy once again. If you think of an analogous thing that both delivers and stores power, yeah, my slinky. But in this case, we're not talking about it the same way we were. We're just talking about it in terms of a spring. A spring can do that, right? Because a spring can store power and deliver power. Why? Because you can cause it to stretch, and if you let go, it shoots power. So you pull it, and it'll store energy and potential energy. You let it go, and it springs back. Okay. A spring constant is something we talk about in physics quite a bit. It's part of an equation of motion. Okay. So if you think of a spring, and as it delivers power, right, it does one thing. But is it, if in a case of this case, I'm stretching the spring, but some springs like to stay unstretched, and then you push them and hold them, and then they spring forward, and you push them back, cock them back, and they spring forward, right? That's another way that springs deliver power. And so it's the same kind of idea, not mechanically the same, but in a thought experiment, it's the same in the sense that you can the same system both stores power and delivers power. Well, that's a power system. That's an RCL circuit. Okay. And so when you think about it from the power triangle, this is the mathematics side of things. The apparent power of something, which is this long hypotenuse of this triangle, is actually longer than either the true power or the reactive power. The true power is if that spring is, let's say, we've pushed it back and it's delivering, right? You're stretching, you're pushing it, and you're making it, cocking it back, and then you're delivering the power. That is the true power, okay? That's delivered power. When you push that string back and it goes boink, and it shoots out, it gives you some kind of force. That would be the true power delivered, okay? The reactive power is how much can you stretch that spring and make it store that energy that you just pushed into it, okay? That's the reactive power. And the apparent power is both, kind of when you add it up in a sense. It's not linear, it's there's a relationship. But that apparent power is going to be higher than either the power that you can deliver or the power it can store, okay? And there's a relationship, as we call it, the phase angle, and that's dictated by voltage and amperage, and we'll talk about that more in a sec, okay? And again, I went over this in far more detail before, but if you're interested in what the power factor is, okay, that's kind of the relationship. And you can get a phase angle, and that phase angle, which is basically the angle, the shape of that triangle between the true power that's being delivered. So this is the power that people use in the power grid. This is the spring, shooting out. And the reactive power, this is the power that is stored, that's you pushing that spring back, okay? The relationship between how much of that power, how much reactive power you have or how much true power you have, defines this phase angle, okay? So if you have a lot of power that you're delivering and very little power that you're storing, you're going to have a triangle that has that's really low to the ground, right? You're going to have an angle that's really low. But if your reactive power grows really tall, then the amount of true power you deliver is pretty small. You're going to have a much bigger phase angle. And we'll go into that in a sec, okay? But it has everything to do with this, what we call the RCL circuit, which basically, in a nutshell, defines how a power system works. So in a system, how that spring, how this analogy works, is that you have voltage and you have current. Remember, we talked about current, right? We already talked about this blue line when we looked at this. Okay, that's that blue line, right? Now, in a normal circuit, that blue line does what it does. But when you have a GIC, you've got this really funky bump-on tail, right? And it shifts everything over, and it's got a kind of a weird issue here, right? You're storing, this is storing power. It's giving you free power, right? But it's shifting things. So what's happening is that you're going to get a shift in this current. It's going to shift, okay? You're going to shift that frequency. Well, when you have a current that does this, alternating, you also have a voltage that's alternating, okay? And here's that phase angle. So we talked about that phase angle just a moment ago. Here, this phase angle. Remember I said that phase angle is determined by how much true power you have that you're delivering compared to how much power you're storing. That phase angle is determined by how much are you pushing that spring in, Okay, if we assume that this is a spring that likes to be unloaded this way, and I push it back, and I'm pushing it back so that it loads that spring, okay? The more I push it back, the more reactive power I am demanding, I'm creating. Okay, this line gets longer. But the more I push it back, the less true power it can deliver. So this is what I showed you last time. Come on, there we go. So as I move, as I'm loading that spring up, and I'm giving, you can look at that loading of that spring, push, 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 push. That's a geomagnetically induced current. It's loading that spring, it's forcing more energy into that spring, in a sense. It's forcing more energy by trying to get it to store more energy than perhaps even it wants to, okay? Well, what that does is it shifts this phase angle and makes it bigger. The problem is power, true power, which I've got colored in yellow, can only be delivered, okay? So in other words, this is power that you are giving out to your, to the distribution, to anybody who needs it, right? Run the camera, run the lights, run the sound, right? Run all of your YouTube stuff that you're watching right now. That power can only be delivered when both the current and the voltage have the same sign. So here we are, here's the zero line. We're in an alternating current and voltage configuration. And believe it or not, in your power system, the power that's delivered to you out of your plugs, the voltage and current are not completely in phase. If they were, both the red and the blue lines would lie right on top of each other, but they don't. They're shifted by a phase angle that's dictated by how much power, how much storage is in that spring. How much are you trying to store energy in that, okay? But the true power can only be delivered when voltage and current go the same direction. Well, that's all in this case. You see, voltage is coming down, current is going up, same sign, they're both positive, so you're getting power delivered here in this triangle. Let me go back one before I do that, okay? This is in a normal system, right? Everything. So you've got this much where power can be delivered here. And then you've got to wait, current goes up, voltage goes below zero, right? So the opposite sign, opposite sign, opposite sign, opposite sign, opposite sign, until we get to about here, where suddenly current now is negative, but voltage is already negative. Voltage has been negative all during this leg, right? So now current has finally turned negative. We can deliver power again. Sadly, voltage is leading. Voltage is going to go to zero soon. So by the time current gets down to here, voltage is already going positive again. So we stop delivering power. So we can only deliver power in these small areas, okay? This is the true power. The apparent power is all of it, right? So it's much bigger, but you can't deliver because you're busy storing the power. Okay, so it's like a spring that's kind of being forced back. It can only deliver a little bit. It has the potential of delivering a lot more, but it's being forced to store energy, so it can't deliver as much. When you put a GIC in the mix, you're shifting this relationship. Look what happens to the little triangles. They get smaller, don't they? When you make that phase angle go big, there's normal, big, normal, big. I'm just showing it back and forth. Not that it goes back and forth, but it's just, if you were to shift it and hold it out, do you see how that triangle where the yellow is gets smaller? Here's an example. It cuts to about here, right? Well, that's what happens. You're forcing the spring with reactive power. You're forcing more reactive power into the system. You're forcing that spring to get more and more tight, which is reducing the amount of true power you can deliver. Can you imagine if this phase angle got all the way to where this triangle disappeared? Guess what? Grid collapse. What is the analogy? You push that spring and it heats up. You push that spring and it heats up. You're lowering the amount of true power you can deliver because the spring can't spring back as much. You keep pushing and it keeps heating up. You keep pushing, it keeps heating up, delivering less and less and less power and getting hotter and hotter and hotter. And finally you push it so hard, it fuses. And now it can't deliver anything. That's a transformer meltdown. Neat analogy, huh? Does that make sense? I thought of that, it was like, wow, this is kind of cool. I mean, it's not the same mechanics. Obviously, your power grid is not a slinky. But it's the same kind of idea. Does any of that make sense, guys? My chat has completely stopped. So I don't know if you guys are enjoying this or completely lost. I am waiting. Uh-oh, I hope I'm not. Oh, good. Okay, people are talking. Good. We may see grid collapse needs to be hardened. Yes, we do. So if grids were solar, well, you know, excuse me, it's hard to say. I don't know yet. I don't know the specifics of how we couple the green energy bit into this. All I know is that if you have geomagnetically induced currents into your system, you're going to automatically have less reactive or have more reactive power load. You're going to demand more reactive power. And that means less ability to deliver power. And if you start taking these transformers offline, you're taking the springs offline. And now the other springs that are left in the circuit, they got to do more. They get slammed even faster. So they'll fuse even faster and the grid will collapse, which is what happened in 1989. Yeah, does that make sense? Great explanation. Oh, good. Good, good, good. You're mesmerized. I hope that's good. Fantastic visual explanation. Oh, good, 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 good. Because this is so incredibly important, but it's so challenging to understand in a non-expert sense, right? And I mean, if there are any grid experts out there, you're just probably pulling your hair out going, oh God, she got so many things wrong. But it's something, because reactive power is such a challenging thing, you know, and the transfer between potential energy and kinetic or delivered energy is really hard to grasp sometimes. Okay. Let's see. Is it possible to use the backside of the nearby moon to extract black material? What in the world are you guys talking about? That is so different. The induced DC current forces a phase shift. Yes, it does. Because it's forcing the grid to take power. It's forcing the reactive power to grow. And I wish I had my iPad with me. I don't have it set up today. But what I would do is draw a triangle, right? I draw a triangle that has this leg go up because the reactive power leg grows. So as a reactive power leg grows, the whole phase angle, the whole thing changes. The shape of this triangle changes, okay? And that causes that phase angle then to change, because you end up shrinking the amount of true power. So this leg gets smaller and this leg gets bigger. And if you draw a small, leg here and a tall leg here, and then you connect the two, it's gonna be a different shape of a triangle, right? Of a right triangle. And what changes is the phase angle, not just the lengths of the sides, but also the phase angle. Okay, and that's what's happening, because you're forcing these sides, these storage sides, to work harder with that free energy. It's being forced to store energy. You never knew power grids were springy, did you? But they are. They're springy, which is great because they need to be resilient, right? They need to be able to handle things like that. It's smart to have grids that are springy. If they were completely, rigid, they would collapse all the time. But they're springy. They can handle power fluctuations. This is how you ride out weird stuff. This is why you can get brownouts and then the grid doesn't completely go down. The grid is springy. But what makes it springy is that reactive power, the ability to store and then deliver more if it needs to, okay? The problem is you're forcing the grid that was only designed to store so much and of a certain kind. You're asking it to store something it is totally not designed for. And and that's why it needs to be a big grid. The grid, it needs as many little springs as it possibly can to help, to help store that energy that it's forced to store because of its design. And if you don't have that, if you start taking your springs offline, this is going to happen faster. Okay. All right. What other excellent way of understanding? Oh, good, good, good. Yes, that's what I was trying to do. Does shorter transport lines benefit? Yeah, it does. It depends upon how they're done. Because sometimes when you couple them together, if there are relays or certain things that couple those lines together, they can be susceptible. But we are much more robust than we ever used to be because we don't have those huge hundreds and hundreds of miles of unbroken transmission lines. We have things, substations and things that stop it, so that in each line, there's not nearly as much induced current, and therefore the spring can handle it. It doesn't end up fusing. Verifying OneDrive. Okay, don't know why it needs to do that now. Okay, it becomes a straight line with only reactance. Exactly. And so it takes something, you know, everything becomes all reactance, and it cannot deliver power. There is no power delivered because this triangle goes to zero, right? Because basically your voltage and your amperage are completely out of phase. When voltage is positive, amperage is negative, and they both peak at the same time. They just peak oppositely, and then they cross through zero at the same time too. And so you just never get, it's just 100% storage, which is great if you didn't have to have anything drawing power. And it was great if these springs could handle the heating that would be involved in that. But they can't. They're not designed for it. Okay. Ground conductivity would be a really cool map. Hey, you're going to see some of that. Actually, I did show some of that last time, but I'll show some of it again because that's really critical to one of the data products that's the Space Weather Prediction Center has. And so, Ash, you're going to see that, okay? You can see it all anytime you want to when you go to SWPC. You just have to know where to look. Okay, good. I think I need to rewatch this after a few beers. Have at it, man. I think that's great. Yeah, you know, take it in pieces. And that's what I tell people, if this is especially if this is your first mini course. I do these only once a month, typically. I mean, I haven't done one in a few months, but I explained why earlier in when we first started this course. But typically I do them about once a month. And so what they are is essentially a month worth of training, right? So you get 3+ hours of training. And so you really need to kind of take it in pieces. So that's why I break and ask for questions, is that when I break and ask for questions, that's a good time to say, okay, had enough today, shut it off and I'll catch the next bit. But some of you guys are crazy diehards and will sit with me through the whole thing. But these courses typically end up being about 3 to 3.5 hours before we're through. Okay, so research into GIC effects. We're still working on this, and I did talk about this last time, so I'm not going to go into it. But what I did this time is I highlighted a couple really big parts, because I want you to look at this. This is something that we're really beginning to get into, and I'll show you a couple papers on this. That GICs are different at different latitudes, and you can understand that now, right? Because of the L shells, right? So that if the magnetic field of the Earth is wiggling differently at different L shells, then it's causing more wiggles at higher latitudes than at lower latitudes, typically, or at least differently. And therefore, you have to look at power grids at different latitudes in a totally different way. Right? So that's something that we're seeing a lot more research into now, which is really nice. So that's one of the things in the science that we're seeing. And then the dissolved gas analysis, what we call, I think it's called DGA. You can look and see by looking at the different gases being liberated in these oils, because remember, these oils are petroleum. So there's lots of carbon-based stuff that you can liberate and create chemical reactions to liberate when, in these oils before the oil breaks down completely. And knowing what chemistry is occurring, and a lot of this chemistry is reversible. So knowing what chemistry is occurring helps you not just know, like, obviously what temperature the gas is. You can measure the temperature, but you can also see how healthy how healthy the oil is. Because once you start liberating certain gases inside that oil, that can make it that much more, much bigger potential for explosion, right? And complete breakdown. So I think I talk about that next, just for a second. I am not going to go into this again. But for those who are interested in knowing more about DGA, here it is. There's something called the Duval triangle that talks about which gases are being liberated and how much of a risk it ends up being, and what zones, as you can see, from D1 through T3, T1 and T2, you can see this, and then they talk about what zone it means. If you're going to get thermal faults all the way up to discharges of high energy, right? Because certain things will conduct electricity and allow because you're driving electricity through this transformer, remember, that are supposed to be insulated, but liberating certain gases actually cause the potential for discharges to increase, okay? And here is the plot that I went over last time, where we're talking about temperature. As you go up in this area, you've got these different gases that are created or liberated: hydrogen, methane, ethane, ethylene, and acetylene, right? You remember light bulbs used to be made, light bulbs. Lanterns used to be acetylene lamps. They stopped using it because it was highly explosive. But you can see as your temperature goes up, they start, what they're trying to show is not only the creation of these gases, but how quickly they're being created. So for instance, methane is just barely being created, but it accelerates. You get a heck of a lot more methane production up to about this temperature, which I don't even see labeled in here. It's somewhere above 200 degrees C, like 250 or something. And then the production of methane slowly goes down as you continue to heat it, but you still get methane liberation. Hydrogen gas just continues to be liberated more and more and more frequently, and faster as you go higher. Acetylene barely begins to take root until you get to about, 700 degrees C, and then it's almost explosive how quickly you start liberating acetylene. So taking an assay of the composition of your oil inside your transformers at any one time can tell you the health of these transformers and how close you are, where you are in this fault tree, this fault triangle, to determine what dangers you might be facing, which is really cool. Oh yeah, and I did have wet transformers. This is for dry transformers, guys. Obviously no water's in here, right? And you know that because what they're talking about are things at 200 degrees C. Do you see what I mean? They're talking about hot spots at 200 degrees C, 300, up to 700, 800. Where does water boil? Right here at the very front edge of it, right? Right here, like 100 degrees, right in this front edge. This, I think, says 200 degrees C, so water is like over here. This one says 65 degrees C. So here's 65 degrees C, and here is, what is this? This is 100, what does that say? 150? That's 150 degrees C. So between these two lines, that's where water boils, right? So this is definitely a dry transformer that we're talking about here. We're not talking about a wet one. But you can have, with wet transformers, I'd love to see this DGA analysis be redone for a wet transformer. That would be, maybe I'll go look for that at some point. But that's why wet transformers are so much more a problem. And I won't go as far as to speculate how many transformers of ours are wet transformers as opposed to dry, but I will say I believe it's the majority. From what I've been told, it's the majority of transformers out there. So that's kind of frightening. And we're talking about the big, kilovolt, 7,500 or something kilovolt transformers. That's what these analyses are for. And here is the paper. I did talk about that last time. So if you want to know more about this type of analysis, that's a good place to start. Okay, so thank you, Jeff Goulartz. Okay, so let's start talking about, we're getting close to being done with all the heavy, I've already done the heavy review. We're going to start kind of easing into the good stuff, where we start talking about comparisons. Okay, so 1989. Now, I am not going to go and play all the movies again. If you want to see the Kappaman review, boy, that was, John Kappaman, when he did his review of the 1989 event and went over all the details, it was really nice. And that can be found on YouTube. It also can be found because I replayed it in my course, where we talked a little bit about it and put it in context with some of the other things we've been talking about. So I'm not going to go over that in great detail. What I'm going to do is kind of hit a few highlights. Also, last time I talked about the kind of a redo of the electric field, magnetic field, and the electrical grid for that particular event. One of my students did this about a year ago, and Cameron Gonteski, and she did a great job showing how the magnetic field and the electric field were changing And during the March, 13th, I think she did the days was like 13th through the 15th or something. Um, and you could really see how all of how much changes or how many changes the magnetic field and electric fields went through. We will go over a little bit of that, but not nearly to the degree that we did before. So if you want to see the details of that, definitely go back to part 3 of this course, and you will find it. Really good information. The reason why I have this up this time, and the plot I'm just standing in front of, is just simply something you can get easily off of Wikipedia. It basically has all the spacecraft stuff. You've got the X-ray flux from GOES. You've got, looks like this is energetic particle events. Is that what that is? Yeah, I think so. Yeah, it is. Sorry, writing so teeny tiny. So this is the energetic particle fluxes. So we had not only big solar flares, but we had big radiation storms. Not super important for the power grids. Neither of those is important. But it's important, the geomagnetic storm is important, and that's kind of what you're seeing here. You're seeing actually when the GOES spacecraft went into the Earth's magnetopause. In other words, the heart of the heart of the Earth's magnetic system got squished so badly that the edge of the nice slinkies that we see of this nested L shells disappeared. It went inside of geosynchronous orbit, and that's why you're seeing this hash, is that we were actually in what's called the magnetopause, which is the nebulous turbulent area between the solar wind and where the pristine Earth's magnetic system is. So that's what this is. That's how strong of an impact this particular CME had when it first hit Earth. Of course, then things kind of went back, and then you got back inside the Earth's magnetic system, but it went back in the magnetopause there for a second, as you can see. But this was a big, intense storm, very, very fast moving, and I don't think I even have the speed on here. No, it was just the cosmic ray, so that's the Forbush decrease. Yeah, it's not really not super important for us. I mean, I got this from Power System Operation. That's this whole slide that shows you, once again, someone who's doing power systems. This is a good YouTube channel to watch, by the way, if you're interested in power systems. Not so great about space weather events, because none of this is really all that important when it comes to GICs. This one may be a little bit, just to show you how powerful, how fast moving the storm was. But I would have much rather have seen, instead of stuff at Geo, I would much rather have seen the solar wind and look at the parameters there to see how fast, what the speed of the structure is. Sadly, a lot of times the stuff back in 1989, we didn't have nearly as many Earth, solar wind orbiting satellites, solar wind stationed satellites, because of the science of space weather is just really beginning to ramp up. In fact, it's arguable how well we did, how well we imaged the CME that caused this blackout. But why I have this up here is because I want you to see, like, this is the Carrington class event we've talked about many times. This is the average. Oh, no, this is DST. I think this is DST. So it gives you an idea of one of the indices that looks at the ring current is the index called DST. And so this was the supposed forensics extrapolation, kind of reconstitution of what we thought the DST index would be during this period, during the Carrington event. And these are the DST indices, again, for various storms. The Quebec storm was 650, so not even half of the Carrington class event, but more than the Halloween storms of 2003, where we had a DST of, it should be minus 425, minus 1750, minus 850. Sorry, there's no minuses in front. But we'll talk also about the New York Railway storm, which was actually bigger than the 1989 event. Some people call this a Carrington class event. It's hard to say, but we'll talk a little bit about this storm because of how it relates to GICs. Okay, but we'll talk about it in a few minutes. The DST index, when you see these numbers like this, that DST index is very specific in terms of what it's talking about. It's talking about how much the current system in near-Earth space changed. It changed the Earth's magnetic system. It's not talking about how much did the field wiggle back and forth. That's very different. So we have to be a little bit careful when we talk about some of these numbers. When you see magnetic field, this is in nanotesla. When you see these numbers being bandied about, you have to be careful how you compare them. So like I said, I've only got these up here is because they're comparing apples to apples. We're just comparing DST, and I probably should have labeled this as DST, so you could have seen this. Why do I say that? Because the very next slide, we're talking about 4,800 nanotesla per minute. Well, wait, didn't we just talk about for the 1989 event, didn't we just talk about it only being 650 nanotesla? Right, but that was for the ring current, and that's for an index for the ring current out in space. This is 480 nanotesla per minute variation changes on the ground, okay? So that's much, much bigger, right? So you can't couple certain things straight into other things. This goes back to the Kaplan analysis. This is taken straight from the Kaplan analysis. What he did, and again, if you go to the course on, that was the prior one, so not part 4, but part 3, E3. We talk about these transformers where he did an analysis to find out what transformers are at risk during a GIC that's as large as the 1989 event. And these are all the ones, and he's got percentages on there. So if you want to know more about it, go back to that analysis. But it shows you when we have really big events like that, these big superstorms, it does make a big difference, right? Every single one of these dots that you see, it's one of those springs, okay? You can't take them out. You take out this little group, you take out some of these springs, especially the ones at higher latitudes, because likely it's going to start at the higher latitudes and then work its way down, right? You start taking out those springs, and what happens is it makes the other springs work harder, right? And then those begin to fail, and they've got to be taken out. And then it makes the other ones that are still lasting work harder, until eventually you get complete grid collapse without even trying. So that's why when people say, turn off the grid, just shut it down. No, don't do that. You have to ride through. And that's also when I feel, I don't know why, I don't know if it's hubris, what it is, but power companies, I have yet to get a good explanation as to why power companies don't solicit the public's health during big geomagnetic storms. Because everybody likely has experienced some type of rolling blackout or something similar at some point, right? Or you know somebody who has. And what do? What do they tell you when there's going to be rolling blackouts? What do they tell you? Lower your load, right? Reduce your consumption. Don't wash dishes during the middle of the day. Don't have every light on in your house, right? Help the power grids ride through this. We'll get through this hot summer or whatever, right? Whatever it is. Well, during a geomagnetic storm, what's the difference? Why wouldn't it be just like that? Why wouldn't the power companies and the power consortiums solicit just the average ordinary person's help in dealing with the fact that they can't deliver as much power? They have to have these springs load up, right? So the spring can't deliver as much power. Well, ask it to deliver less, right? Don't force it to deliver more. Ask it to deliver less, because that will help. And so when you ask the grids to do less, then you're actually helping them ride through these things. And so this is one of the things where I really think that we, as just consumers of electricity, can be of great benefit to the power companies. This is also why I want space weather on the evening news, because I want meteorologists to tell people, okay, we've got a big geomagnetic storm, and those in higher latitudes, hey, reduce your power consumption between this hour and this hour. You know, reduce your power consumption, you know, during these next 48 hours, and we'll ride through this just fine. That's what we need to have happen, because we are much more, we are much less helpless. You know, we are much more empowered that way by helping our big infrastructures ride out these things. And we don't have to look at it as Armageddon. It really is a sane way through stuff like this. And we've done it before with other systems. So, sorry I got on that sidebar there for a sec, but what I was trying to say was that this is now a massive voltage, or a massive magnetic field swing in a very short period of time. And what we've learned is that it's not the overall depression of the Earth's magnetic field. It's not the overall magnetic change. It's the little wiggles that make a huge difference. Problem is, a lot of magnetic indices, right, that we use don't capture the instantaneous changes. They're not designed to. We didn't know way back when that, that's important. Swings delta B is important. So this kind of study is now being done, right? This is then British Geological Survey. They have tons of these paper records that they're going back and digitizing because they need to get the swings. They want to understand the swings now, right? Before, we only cared about the big depressions or the average changes. Well, that smears out all the swings. But the swings end up being the key to it all, okay? And not just the swings, but the sustained amount of swings. So in other words, you don't just have a quick swing and then have it be quiet. You have swing and swing and swing, big swings over long periods of time, sustained big swings. So in other words, you need that Earth's magnetic field to rock and roll quite a bit and continue rocking and rolling like a marathon dancer, just let's swing all night long. That's where things become a problem for power grids. Because springs can handle instantaneous demands, right? It's just, are you doing this all night long? Yeah, okay, I'll stop that. Yeah. Oh, Lord, that was funny. Okay. But you have to, if you end up causing too much of that, too much heating, and over long periods of time, well, that's what causes those gases in those transformers to begin to really liberate stuff, right? You cause this type of thing to happen, right? Heat. Okay? Heating isn't instantaneous, it takes time. But the more you do it, the hotter you get. Yes, there's a lot of innuendo here, I get that. Sorry, I can't help it. I'm not trying, I promise. But I guess it's just the way it is. So this becomes a bigger issue when you have sustained swings over a sustained period of time. Okay. So yes, there are people working on this. Antti Polkinen, a good friend of mine, the absolute leader, and yes, his name is Antti Polkinen. He works very closely with the NERC and the FERC, the National Electric Reliability Consortium and the Federal Electric Reliability Consortium, which spreads basically mainly over the United States and Canada, up into through like PGM and some of the other utility consortiums there. But it's looked at by others, including the British, the National Grid in Britain, and some people, and in Europe as well. But Antti's been working for decades on this, and we're beginning to really kind of understand how things are affected, not just by changes in the magnetic field of the Earth during these geomagnetic storms, but also their intensity, their how quickly they change, right? How much they wiggle, and how sustained is that wiggle. So for instance, now we're beginning, and this is in Antti's paper, we're actually modeling the induced currents and the heating inside transformers to try to understand how, so you've got these GICs, you've got lots of them. Look, tick, 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 tick. This is during, I forget which, this was in 2010. I can't remember what storm this was, or I'm not sure if he was modeling a storm. I can't remember, guys, I forgot. My apologies. I remembered last time and I forgot now. Poop. I'm sorry, but I did talk about this last time. I probably said it last time and I just can't remember now. But what's interesting to note is how many of these little GICs you get. You can get smaller GICs that don't go quite as high, right? But if you have them more frequently, you can get a very large amount of heating compared to having just one GIC that's really tall. But it's only one. It doesn't last long. See the heating in the blue? That's almost the same. It's almost the same amount of heating. And you can also get a small heating over a long period of time. A small GIC that lasts over a long period of time, and you can get some decent heating from that as well. So it's not just a function of how big is your GIC, because if that were the case, this is the GIC that would cause a massive amount of heating above all of the others. But it doesn't, does it? You've got smaller GICs that are back to back that cause just as much heating as you see here. Okay, and you've got even a smaller GIC that lasts longer that can also cause a significant amount of heating. So it begins to make you realize that it's not the peak number that matters, but how sustained it is, how often it is, right? So oftentimes you'll find when you look back in history and you see solar storms or CMEs or events that cause grid failures, you know what? It wasn't one event. It's back to back. For instance, the one right here. 1859, everybody goes, oh, September 1859. No, it was two. There were two of them, back to back. Any of you who have watched me talk about bad actors on the sun, right? These are the big sunspots that come in and they're just really angry. I say, and what happens is that either they emerge on the Earth-facing disk or they rotate into view and they fire off a storm, and then they fire off another storm, and they fire a big solar, X-class flare, and a radiation storm, and a CME, and then a radiation storm, and then another big flare. Boop, 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 and it's just machine gunning all the way across the disk the 2 weeks that they're there. Okay, because it takes about 2 weeks for these regions to rotate off of the Earth-facing disk. And they just constantly are firing something one after the other after the other. And when it gets into the Earth strike zone and they fire off multiple events, well, we get clocked. Earth gets clocked by big events over and over again. And that's exactly what happens with these Carrington-class events. When we have them, oftentimes it's not just one, it's several. The Halloween storms, same thing. There were 2 or 3 of them that hit us back to back. And it's the sustained length of time that Earth is being assaulted that causes the problem. Okay, so I keep seeing this so often where people are oh no, it's a G3 level storm watch. Oh gosh, we're scared. It's going to be awful. It's and I have to go in. I'm sorry, we're thinking cats and dogs living with you, writing. I'm thinking Ghostbusters, right? Cats and dogs living together. It's going to be mass hysteria. The issue is that it's just one storm, and we won't know until it hits us how large it is, especially if it's a glancing blow. It's probably not going to last that long. I mean, we've even had Carrington-class events graze us. Back in 2017, you may not know this. Back in 2017, we had, in September of that year, we had a Carrington-class event, or near Carrington-class event, graze us. And it brought us to a G1 level solar storm for about 6 hours. And it was the flank of this thing. I mean, this was a massive storm. But guess what, guys? It didn't last very long. It would have, had we hit the middle of this thing, holy crap, it would have been a G5, no question about it. No question about it. But we just barely hit the hairy edge of it. And it didn't last long enough to really bump us up. I think the whole thing lasted 6 hours. But it was like, wow, this is a big CME. But did it make the news? Nah. The flares did, because they were the biggest of the cycle 24. But the CME didn't. So, there's a lot of things that have to happen in order for these events to cause grid failure or grid stress, okay? And we're learning a lot more of that. And Auntie and his crew are on the leading edge of that. Here is, for example, the mapping of how many magnetometer stations now are measuring real-time dB upon dt, right? Change, time-varying change of the magnetic field. So the derivative, the first derivative of the magnetic field. So instead of just measuring the magnetic field and leaving it alone, actually measuring how quickly is it changing, because that's what matters. As we're finding, that's one of the things that matters. Okay. Another paper. This is by Oliveira. And what's cool about this one, latitude. Look, high magnetic latitudes, mid-magnetic, low magnetic equator. They're looking now at the latitude dependence, which is super critical. One of my good friends, I believe, is in here. Well, a lot of my good friends are. Brett Carter, for example. Eftahia is in here. Zesta. Jimmy Rader is in here. I know these people. Lexa Halford. These are wonderful people. Bruce Tsaritsani. Wonderful, savvy people who understand this kind of thing. And Brett, who's in Australia, they worry very, very much about EMP during big solar storms because they worry about these big CMEs doing exactly what we talked about, where I said the two magnetic fields are aligned the same, but they bounce off each other. That compression, when they bounce off each other, remember magnetic fields are also springy, you can actually cause that bumper car to have a huge compression of the Earth's magnetic shield. Well, that also is a change in magnetic field over time. It also induces electric potentials. That can cause an EMP, what we call the E3 component of the EMP. But that bounce happens at the nose of the Earth's magnetic system. And what they're talking about in this paper, as a matter of fact, EEJ current. This is the equatorial electrojet. Okay, so we actually have, just like we have electrojets that deal with at high latitudes, we have the eastern electrojet and the western electrojet. We also have equatorial ones, but the equatorial electrojet is mainly around noon. So they have actually taken these magnetometer stations and looked at different events, and looked for events at low latitude, looked at magnetometer stations at low latitude, and were able to sample and see the equator electrojet being intensified. So, because that's super important for these guys down here at low latitudes. Okay, so we're seeing papers like this now where people are looking at GICs and they're looking at EMP and they're looking at all these things that big storms can do, but they're looking at it with the savvy eyes of people who now understand how this stuff couples in. And you're getting, and Brett, for example, he's an ionospheric physicist. Alexa, I believe, is a magnetospheric physicist. We're getting lots of cross-disciplinarian. Jimmy is definitely a magnetospheric. But Surasani, I've seen him do solar wind stuff. So it's really cool that we're getting cross-disciplinary work going from sun to mud, which is really what we need to do when we start talking about effects on the ground and how these things affect operational systems, right? So we're getting much, much more savvy. But again, we need to have ground-based magnetometers that are measuring the change in magnetic field, not just the peak. So we're going to likely, and I'm hoping soon, we're going to start seeing new indices being put into play. And as soon as they come more online, and we're sure we're going to see them, I'm hoping that they're going to come online and I will start using them. Because we need to have those kinds of indices that are paying attention to the changes. And indices, we already have indices that are latitude-based. But now having indices that are latitude-based and are maybe local time-based and are also, well, not local time, that won't make any sense, but latitude-based and are delta B, time varying, ones that look at the first derivative of magnetic field changes, right? So they're looking at the changes over time as opposed to just looking at what the value of the magnetic field is at any one time. They're looking at how it changes from point to point and measuring that and plotting that and making that available to us. That is where I think some of the magic's going to happen, where we're going to start really putting pieces together and be able to get a better feel for how much more dangerous things can be, and when to worry and when not to. So, just so you know, the G scales, which again is based on KP, right, which is not a time-varying indice. I mean, it's time-varying, but it's not looking at the change of magnetic field over time. It's not a delta B thing. It's just a B. So you're looking at the G scales that NOAA and SWPC puts out, but you're seeing it kind of really how it's been modified specifically in terms of the impacts on the power grid. These are slightly different than what you actually see on Space Weather Prediction Center's page. So, people are paying attention. And I think I talked about that last time. And I think, let me pause because we're going to get into now the comparisons. Yeah. Just seeing how many slides I have left. Yeah, it's all comparisons from here on out. So let me pause here and see if you guys have any questions. Where am I? There I am. How you guys holding up? We're 2 hours into it. How you holding up? And we're about 2/3 into the course, so this will be about a 3-hour course. Fun fact, if you've passed high school physics, you can benefit massively from watching. Yeah. Oh gosh, yeah. Yeah. I try really to make it conceptual. You know, I mean, I will go into some of the mathematics just a teeny tiny bit sometimes, but it's always an optional thing. It's never critical. I should always be able to find some way of analyzing, you know, making an analogy for you. Earth-directed flares occur at an anomalous rate. They shouldn't, you know. Oops, some things are scrolling faster than I can read. Okay, let's see. More heart and strokes issues during high solar activity. That, believe it or not, is strangely true. Well, you know, I'm looking through medical databases and we're seeing stuff, more and more stuff about that that's peer-reviewed. Blood has iron in it. There's issues with viscosity, things like that they're finding. Coagulation, platelet formation, these types of, or platelet, you know, activation in a sense. Things that change the viscosity of the blood when Earth's magnetic field is rocking and rolling. It's very interesting that I'm seeing these same types of repeatable results over and over again in medical journals. I think this is a field that's going to explode here very soon. Because people are really beginning to wake up and they're being able to find people that do not go to astrobiologists to understand Earth's magnetic system and space weather. Go to heliophysicists to understand, and magnetospheric physicists to understand this stuff. Do not go to an astrobiologist. They don't have the right expertise. So if you are a medical practitioner and you just happen to be watching, astrobiology is not the right place to go. You need to go to heliophysicists because we talk about what's happening here on this planet. And you will get far better expertise from heliophysicists than you will from astrobiologists. They look at the stars. They don't look at home. We look at home. That's our bailiwick. So that's partly why that miscommunication or that lack of cross-disciplinary studies when it comes to the medical field and space weather physicists is because they don't know. The medical field has been asking. I've seen papers where the medical field says, please, astrobiology, anybody out there, we want help. We want to understand this better. We want, you know, criticism. We want, you know, collaboration. Come talk to us. And they get crickets. Well, for obvious reasons. The astrobiologists, they're out studying, you know, life on other exoplanets and things like that. They're not studying what happens with space weather here. It's just the wrong expertise. So I'm hoping that we're going to kind of, as we raise awareness of what space weather is and what's being affected and what is in that sphere of influence, that a lot more medical professionals will say, oh, and the medical researchers will go, oh, you mean I need to ask you guys? Yes, ask us, and we can help you, you know, maybe craft your studies in such a fashion that makes sense, that it would pass peer review, because it's hard. I think right now there's a lot of studies out there that would, if you were to put a heliophysicist in the mix, they'd go, I don't think you can make that correlation. So it's a field that's just beginning to study or beginning to blossom. And again, it's one of those fields that's kind of a fringe field, but it's beginning, you know, you're seeing a bit more of that, you're beginning to see it move closer and closer to mainstream because more and more of those studies are being funded. But it's just starting. So, okay, this is the best part of your day. Oh, Heidi, that's sweet of you to say. Oh, you guys are still here. Good. You are completely in for. Oh, you out of here? Okay, bye, babe. You guys are absolutely glutton for punishment. That's all I can say if you're still here. But just know you don't have to watch the whole thing all the way through. You know, that's why I take breaks and stuff like that. Okay, doing well. Doesn't ever seem long. Oh, that's good. I'm so pleased, Stephen. That's awesome to hear. David says, thank you, Tamitha, for explaining things such that people with all the levels of learning or walks of life can easily understand. Yes, and that's just it. I mean, this stuff is intuitive. It really is. I mean, we can understand these things. It's just a matter of finding the right analogy, finding the right context. And you know, there's everybody is smart. Everybody's able to understand this stuff, and especially if you don't have to understand the mathematics that go with it, you can understand the concepts without necessarily being fluent in the math. Because you know, we all live on this planet, we all live in this world. We see things every day in our own experience that teaches us how life works, and this is part of life. So we can find ways of communicating it. Okay, let's see. FYI, hemoglobin is a tiny, tiny portion of the blood mass. Doesn't matter, you know, it doesn't seem to matter. You know, other people, I know people who have heavy metal poisoning, and they put their cell phone up to their ear, and they will get rashes on their face and on their hands that was holding the cell phone. And some of them have like mercury poisoning and stuff like that. I've seen it firsthand, no pun intended. And yeah, I was one person I actually even said that to. She told me about this, and that she had got rashes anytime she was EMF susceptible, like you know, very susceptible to electromagnetic fields. And I said, do you have any heavy metal poisoning? And she says, yes, actually I have mercury poisoning. I said, well, that's it. That's why. It's because you've got heavy metal contaminants in your blood. You're going to be more susceptible. And that means you're also going to be more susceptible to things like geomagnetic storms. I mean, people who have plates and screws and, you know, things that, I mean, there's just all sorts of ways that you can become space weather susceptible. I've just seen too many people that are that way, that have the same kinds of things, and they have the same types of symptoms as well. There's something there. There's just something there. I think that a lot of that's going to be revealed over the next maybe 50 years or so. It may take a while. Medicine and research moves slowly, but I think we're beginning to see it coming out. Oh, thank you. Thank you for watching from the UK. I know it's late over there, so I appreciate that. Oh, good. Thank you, Bumfezzled. I'll call you Oxter. That's cool. I appreciate you being with us in our Patreon community, or at least on YouTube. That's very kind of you. And Spirit, I'm always in for the long haul. Thank you so much. I'm glad you guys are hanging in there. Oh, a lot of you are tuning in. Nick is tuning in from the UK as well. Good, good, good. What can we expect from the next solar cycle? You mean the one we're in, Heidi? Or are you talking about cycle 26? Cycle 26, don't know quite yet, but we already are seeing the signs, so it is coming. So anybody who's a grand solar minimum enthusiast, I hate to say it, but I don't think we're not gonna lose sunspots anytime soon. I don't know if it's going to be stronger than this cycle. There's a chance. A couple of us are thinking that we're in the Dalton, like a Dalton-like minimum right now, and we may be pulling out of it. Oh, great, happy birthday, turned 41 today. When I was younger, it seemed that all had been done, and now just learning how much there is to learn, right? Sitting in a tractor, gathering bales to feed cows while learning space weather. Hey, isn't that great? I love technology because you can do that now. And if you are in a tractor, then likely you use GPS. So thank you for being here. You precision agricultural people, you have alerted me many times to issues with GPS, and I appreciate it very, very much. Spirit, I didn't know you were in the Redwoods of California. Awesome. You're just north of me then, likely. Okay, it looks like everybody's good. Vegan said, how rare does sunlight hit the bottom of Olympus Mons? I don't know. Olympus Mons it's mid-latitude Mars, so you know, Martian seasons, of course, are longer. So during the Martian summer, I would think it's probably does pretty well. During the Martian winter, it may not get very much sunlight. It all depends. But remember, the Martian seasons last longer, and they're different from ours. So, and then of course you have to worry about dust storms, right? Dust storms are an issue because you can get pretty opaque, like in 2018, right? It took out, you know, it took out one of our rovers. Poor thing. Okay. Any other questions, guys? Maybe if you keep scratching your ear, you would. Oh, if you kept scratching your, yeah, but they would get rashes on their hand as well, you know. So there's lots of people who live in those EMF-free zones, typically around radio antennas. Strangely enough, you have this big radio antenna, you'd think, oh, that's going to be really noisy. No, they actually have quiet EMF zones around those radio antennas because it causes the radio antenna to pick up all the noise here. It's kind of like starlight for astronomers. You know, you want to go to a dark sky area. Well, this is a dark, you know, radio noise, low radio noise area to have those radio antennas because they're so sensitive. And people live around them because it allows them to live a cleaner life when they're nasty, you know, when they're dealing with you know, sensitivities to EMF. Yes, I know Olympus Mons is 80,000 feet high, but, well, I don't know if it's 80,000 feet high, but it does have kind of a crater in the middle of it, and I assumed you were talking about inside the top crater of it. Okay, guys. Sounds good. Looks like we're good. All right. So let's start getting into talking about storms, comparing some. So here is, now if you guys remember, those of you who have seen the other courses, here are 3 different indices, okay? And again, if you're not familiar with these indices, just look back at my other courses on the ground, because that's when I go through them. I talk about the AE index quite a bit. It is a high latitude index, which means it is a high L-shell index. This index is dealing with magnetometers that are just below the auroral zone. And so they pick up a lot of things from, you know, those field-aligned current systems we talked about, the westward and the eastward electrojet. And so they go wonky real fast. They're very, very sensitive. They can pick up little substorms, which you see here. And anything, if you look down, so AU and AL are the upper and lower envelopes of the index. AE is if you, AE is the difference between the AU and AL. And then the AO is the average, essentially, of AU and AL, okay? But I typically look at AE, and the reason why is because anything above 500 is considered a substorm or a storm. So here's a substorm here that just barely broke 500. These types of little wiggles will give you aurora at high latitudes, but not down to mid latitudes. They also don't necessarily require anything to happen to the Earth's magnetic, the solar wind. Oftentimes these things can be just internal reconfigurations of the Earth's magnetic system. Something was unstable, you know, and the cool thing is that there are some people now who are studying things like eclipses. And so if you have the Earth, you know, if you have an eclipse and you have the big shadow of the moon blocking out the sun in a small region on the Earth, it can actually trigger a substorm. Wow, that's cool. The reason why is because there's changes going on in the ionosphere and little changes there that in cooling and stuff like that reconfigures things, and that causes enough of an electromagnetic change that then causes something that was really metastable out here in the Earth's magnetic system to say, oh, too much, and then it reconfigures. So you can get these little substorms triggered by all sorts of little weird things in the internal system of Earth that doesn't necessarily have to be solar wind related. And I know that will make people like Larry Lyons very unhappy, but it'll make people like Joe Fennell very happy. So because there's a lot of people in the substorm community who argue back and forth what causes substorms, and some of them assume and argue that they're all solar wind generated, and some argue that they're just internal reconfigurations. So it's kind of neat to see people studying things like eclipses and just atmospheric changes actually propagating out and causing changes. And so, you know, wouldn't it be cool? I mean, here's another totally strange idea, that could earthquakes in a metastable configuration, could an earthquake actually trigger a substorm? And the reason why you say this is because we actually do see changes in the ionosphere after an earthquake. We see changes in the ionosphere. We actually see before and after, because the changes on the ground actually do propagate up into our atmosphere. And so that those ionospheric changes then, which are now electromagnetic, so you go from the ground to the neutral atmosphere to the charged atmosphere. As soon as you get to the charged atmosphere, now you're dealing with electromagnetic changes. And so that potentially could then propagate out to our Earth's magnetic system. And if something is balanced on the head of a pin, some instability is just about to go, could that be the thing that pushes it over and causes a substorm, causes a dipolarization and a substorm? Sure, sure. And for those of you who have no idea what I'm talking about, it's just me going off talking science for a second. But there might be a few of you who might actually look at that and go, that's an interesting thought. So these are the little teeny tiny storms, little teeny tiny things that don't last very long, don't really mean all that much, but they do shoot particles into the Earth's upper atmosphere, both in the north and the south. They can also cause problems for spacecraft charging that go through the auroral zone, and for low Earth orbiting astronauts, right, in the ISS. They worry about these substorms because when these things light up, if they happen to be on an EVA, then they could get high doses of radiation for short periods, which can be very dangerous. So they really don't like having EVAs when the Earth is busy at all. Those are not good things. But in the grand scheme of things, you know, to those of us who really like big geomagnetic storms from big CMEs, this is like, you know, it's hardly anything to blink at. But it still has real implications for lots of things, lots of different assets in space, human or otherwise. But this is the most sensitive of the indices. Why? Because it's at high latitudes, which means high L shell, which means it's way out. It's connected to part of our magnetic system that's way out of the front lines, and always ends up getting bugged first, you know, disturbed first. Now, the second one is actually this one here. This is KP, and this is that mid-latitude index. Okay, now mid-latitude indices means it's kind of got a little bit of this index here, and it's got a little bit of this index here. This index, and we'll talk more about the comparison of these in a second. This index is DST. Again, not one I'm going over very much, but this is the one that goes with the ring current. Okay, and when we talked about those dips, remember I said like the 1989 event was 650 nanotesla, the Carrington class event was a 1750. Yeah, we're talking about DST dip. This is how much did the ring current change the Earth's magnetic field overall. When you energize the ring current, it actually creates a magnetic field that actually reduces the overall Earth's magnetic field intensity on the ground. And so that's what you're seeing, is when you get a big geomagnetic storm, the ring current dips down. When you get little teeny tiny substorms like this, nothing. Just bumps and wiggles, nothing. But when you get a big storm, which is what you see here, right, where this goes basically off scale, because it's a big storm, you get a nice, you know, not huge, but okay dip, minus 100. Okay, this is because this is at lower latitudes. The ring current is well inside the Earth's magnetic system, lower L shells, therefore more protected. It takes a long time to heat up that ring current, and there's lots of reasons for that. Part of it's because it's deeper in. Part of it's also because it's the energy storage of the Earth's magnetic system and particles, and so it takes a while to make this energize, and you have to have something reasonably sustained and strong. So a substorm isn't going to do it. Okay, so that's the DST, and then KP is a little bit of this, so it can pop up faster than watching DST, but it also isn't going to get overwhelmed like AE. So it has some of this in it too, because it's a mid-latitude index. And as you can see, KP really, when the storm hits, you just see a bunch of hash all the way across. But notice in DST, you see two distinct lumps, 1, 2, right? There was an onset that hit pretty strong, and then it kind of died off, and then it came back, okay? You don't see that in AE. AE was just rocking and rolling hardcore the whole time. But you do see a bit of a two hump signature here. Does it go all the way down like this did, almost back to you know, like 50, you know, almost nothing? No, it went only to here. It barely stopped being storm level for a short while. This is KP of 4. It almost was completely storm level all the way across, which is KP of 5. But it did have two distinct humps at KP of 8. So this was a G1, oops, KP of 5 is G1, KP of 6 is G2, KP of 3, or KP of 7, sorry, is G3, KP of 8 is G4. This, in September 8th of 2017, is a G4 level solar storm. Okay, it's a big storm. Did it last that long? No. Less than a day, about a day, right? From September 8th to September 9th. Didn't even storm. And the most intense part of it, these are 3-hour bands. 6 hours here, pause, and then the most intense part of it, another 3 hours, and then it wind it down. And that winding down, when you see it going down like that, that is showing you that things are really beginning to let go. Sometimes because it's a 3-hour running average, what happens is that you can actually turn off the source and just coast, and it will still take a little time for KP to go down because it's averaging. It's a running average. Okay. So you don't always see a shutoff like you do with some of the other indices. But you can see how dramatically different they are, right? So this is really good for small storms, right, but can get overloaded really quickly for big ones. This is great for big storms, but doesn't even recognize when little ones are happening. And this is kind of good for both. This is why KP is like the end-all, be-all that everybody has always used. It's also got a very long history. Do you notice there's not anything about dB by dt? There's no time-varying magnetic field in these indices. It's all just what is the magnetic field value at that time. On the ground at high latitudes, on the ground near the ring current, lower latitudes, or converted into a simple index based on a very simple mathematical formula, which I won't go into, that we talked about in the last, when I went into KP in depth. It's just a simple formula. But it's, again, based on the value of the magnetic field, not based on a time varying, the change in the magnetic field. We don't have any indices like that. During that solar storm, that G4 level solar storm, this is what the change in the magnetic field looked like. Notice that the intensity, this is kind of where some of the auroral oval is in here. You can see part of the, this is what the westward electrojet at that time. Notice that the intensity of this storm occurred over the Atlantic, not necessarily over the United States or Canada. That does make a difference. When the storm impacts and when it reaches the highest intensity, where is it, right? What time of day is it? So midnight was over here. So this was in the early afternoon for Earth. And so it really does matter what we call local time, what time it impacts. But as you can see, this is over 400 nanotesla change over, and I forget how quickly they average this. If they do this per minute I have to go look back and look, I forget. But you are seeing that the intensity of this thing was not over a landmass, which is what I wanted to show you. But you can also see how far down it came, okay? If this had been shifted over, would it have been a bigger deal? Yeah, sure would have. But that's one of the things that you have to take into consideration when you're talking about storms. If the storms happen quickly, right, and you only have a peak over a short period of time, well, this, by the time it rotates fully over here, the storm's already over. So is it going to cause a huge GIC problem that lasts? No, right? So when the storm hits, that's important. How long does it last? What are the changes that occur? How strong is the magnetic field change? Right? All of these are factors when it comes to big geomagnetically induced currents. You have to have something like a perfect storm in order to have these big impacts that really can take down grids. Now, someone, I think it was Smash, I think you asked me, oh, it would be cool to see conductivity maps. Well, here you go. Here is a conductivity map. This is from way back when. This was done, and I think there are new ones now I just need to update because I'm not going to concentrate on this storm. But this was when the conductivity maps were just beginning to be done. And so what you're looking at, since you can see this was an experimental prototype way back when, but this is for that same storm. And this is where we start getting into not just the latitude dependence of GICs, but also the geology, right? So we talked about geography, we talked about latitude, and we also talked about geology, meaning what is your bedrock made of? And so when the assays were just being done, they had conductivity maps that they were using at the time. This is, like I said, a few years ago. And so they were just kind of beginning to work this model out. And as you can see, we actually had electric fields over 500 millivolts per kilometer with this storm. And the intensity, and this is an average, but the intensity of it was mainly here. Much, much stronger at high latitudes, but also because the bedrock is more conductive here. Okay. So you had that issue. You can also see that that's why you had peaks in this region, as you'll see in the much more, much better refined maps that you'll see very shortly. You'll see far more of a band going across this region. And you'll see a little bit of a band going across this region, because these are going to get a lot better. But I just want to kind of give you an idea of what the voltage was from that. One of the peak voltages was about 500 millivolts, 550 millivolts per kilometer. And that goes along with what you see here. Okay? Reasonably short term, not really lasting. Now, if this were solid KP of 8 all the way across, would we see the same? Not at all. We'd see much, much stronger. But this is essentially a two-peaked storm, right? You can even see it in DST. Had a break. Okay? It wasn't less. This is in a sense it's a GIC breather, right? It let them have a break. Didn't let them have a break at high latitudes, but yeah, high latitudes, that's not that big a deal. That kind of stuff happens all the time. But when you get it down into mid latitudes, woo, then you can get some really strong magnetic field issues, because you're in lower and lower latitudes where the magnetic field is stronger. All right, am I ready for that? Yeah. Okay. So that was a storm from 2017, one of the storms from 2017, during that hellacious period where we had Irma and Marie and Harvey. It was where we had the two largest solar flares of solar cycle 24, where I actually, for the first time in my space weather broadcast career, was going, oh, I'm not liking my job right now. And amateur radio operators were groaning, saying, Tamitha, make it stop. And I'm like, I'm trying. Because we just had a bad actor that just would not stop. And that was one of the solar storms that it launched. Thank goodness it was only one at that time that hit us. And it didn't let out its Carrington class event until later, it's September 10th. And that only grazed us, thank goodness. But it is a different story. Okay, so let's talk a little bit about the March 1989 storm. Now, again, and I'm not going to play them again. I played them at the time because it was important that I play them during the Kappaman analysis so that you could see the updated analyses that are done. If you want me to, I will play them again. But they are the movies that show maybe I'll play one. Maybe I'll play the one that has the electric grid, so you can see the electric, how the intensity of the field and the currents that were induced in the electric grid, how they changed over time. So I might play that for you here in a minute. But let me get through this part because I want to show you this. Okay, so these are the data for this, for all of the same indices. I'm sorry I don't have a funky little plot that looks like the other one. The reason why is because it's older data from 1989, so I just have archived data. But don't worry about these. I just pulled this down from the website, so don't worry about these because these are SIMH and ASIMH, which is very similar to like DST. What I want you to look at is the red plots here, which is the AL and AU. They don't have AE plotted, but you get the upper and lower bound. So imagine that as like AE. You add this to this and then divide it by 2. But you can see these numbers are clear in the 2000s, right? So this is a very, very intense period, and it just stormed like crazy through this whole period here. DST kind of went down and went down. Here is like 650. This is, remember we talked about that 1989 event was 650, minus 650 on the DST scale. Yeah, so you can see it on this real-time thing off scale. So that was the peak. So a really intense peak. Here's the KP index, okay? March 13th goes up, here's 9. So here's 8, right? Look how long it's now sustained at 8, bumping up to 9. For how many 3-hour blocks? Essentially 1, 2, 3, 4, 5, 6, 7, 8, 9, almost 9, 10, right? If I can count these that are close to 8. So 10 times 3, 30 hours. We're not talking 6 hours with a breather and then another maybe 3 to 6 hours with a breather. We're talking 30 hours hammered on, right? So what are you doing to those springs? Constantly, constantly hammering, 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 heating, 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 right? Those power grids can't handle the sustained intensity. What's going to the magnetic field? It's doing a marathon dance. You know, this is the marathon swing dance, right? It's just doing this forever and just constantly hard. So it's rocking and rolling big time, and it's doing it for 30 hours straight. Okay? It's trying to win the Guinness Book of World Records for marathon dancing, swing dancing. Okay. Did it break? Yeah, sure. And in this case, in this index, KP of 4 is yellow, but so is KP 5 to 6. Sorry, I've got people in the house. KP of 5 and 6. So 6, even KP of 6, which is a G2 level solar storm, is still yellow. So imagine if this KP of 6 is yellow or is red, and even a KP 5 of G1 is red. So you'd see all of this is still red in through here. This would be red. So don't let your eyes fool you. The scale of the stoplight chart, right? Green is good, yellow is eh, and red is bad. Don't let that fool you, because in this case, the yellow is actually bad because it's everything above KP of 5, which is here. Okay, so you can see some of these yellow. This all here is lit up. This should be red because this here is above KP of 5. I don't know if you guys can see that. It's hard to see on my screen. This is above 5. Okay, so all of this, it was even more than 30 hours. That was storm level. Okay, but KP of 6 is about where the grids really start worrying. But 30 hours at a KP of 4 or at a G4 to G5 level solar storm with a massive decrease. I mean, that ring current was really energized. This is what you get. Now notice this is more refined now, okay? Much more refined. And like I said, I can show you the electric grid, kind of what it went through over the course of time, right? This is an extended storm, more than a day, okay? You're talking about 8 volts per kilometer. What was a September storm? It was just kind of mild with a breather. We're talking about 500 millivolts, half a volt. Here it's 8 volts. No wonder we had grid collapse. No wonder we had springs being taken offline. Now, could we have ridden through this if the grids hadn't been taken down, if the mitigations had been in place so that the protective relays weren't just saying, oh, pull this transformer offline, pull that transformer offline, it's heating, something's wrong, and it kept pulling off the little springs so that whatever springs were left had to take the load, right? And then more reactive power was lost, and more reactive power was lost. And pretty soon, what was left of these springs had to really compress themselves to the point where they couldn't deliver power anymore, right? Could we have ridden through if those protective relays had been in place or had performed according to what you would do with a solar storm, which is don't take the grid offline, don't take the springs off, just let them heat up? Perhaps, perhaps. But nonetheless, 8 volts per kilometer, okay? And as you can see, everything was lit up red. Now, how many of you remember there's a G3 solar storm we just had recently? You guys remember that? This date? It's just a few days ago, right? Not that long ago. So it's kind of neat because we can actually do some comparisons. We can actually look and see. Here's the AE index. We got our nice real-time indices, right? And as you can see, yeah, pretty ratty. We got a little bit of a break. Pretty ratty, right? Here's DST, the preliminary of DST. That's why it's got this bar here, because it's not finalized. But you can see DST, doesn't go down that bad, a little past 100. Okay, so we got a lot of stuff going on at high latitudes. Low latitudes, you know, minus 100, it's not that great, not that big a deal. What did we get for KP? We're at almost KP of 7. So G1 is 5, G2 is 6, G3 is 7. Almost, it was close enough that we called it KP of 7. So it was a G3 storm. How many hours? 1, 2, 3, 4, 5 times 3, 15 hours. No break for 15 hours. Now, notice DST, hold on. I think I'm okay, hold on. Is my mic off? No, mic's not off. Just making sure nobody's trying to contact me and tell me something's wrong. No, it looks like I'm okay. DST, although it only went to 100, okay, which is not very different from this one, in September 2017. There was a break in the middle of this, okay, which we don't get. Here, there was only 6 hours and then a break, and then, kind of a declining, maybe another 6 to maybe 9 hours, right? But you got a nice break of, of maybe 6 or more hours if you kind of look at this being only KP of 5, which is a G1 storm. So which is really not that big a deal for a power grid. Okay, so we have 2 peaks, 1 with a break. That's essentially as intense as this. It's KP a little bit more than 100. Right, well, it's maybe about 125, so a little bit higher peak here. But part of that issue is because we had a G3 storm, but it was solid G3, or pretty solid to a G3, for 15 hours, almost more than a day, or almost 3/4 of a day. Okay. Now, you don't get a breather. It's a lot longer, right? So you'd expect that there'd be more heating, but do you think it's going to be anything like that 30-hour thing that we saw? No. However, I was paying attention. I was watching. I actually snapped some of this. In fact, is this the movie that I took? Watch. See it change? Now, this wasn't even the peak of the storm. This was just shortly after the peak of the storm. And why is that? Well, because I was so taken by aurora photography that I forgot to start recording some of this stuff. I'll play it again. But when I started realizing how strong the storm was getting, I decided, you know what, let me just grab some of this and see how intense it is and if it continues to build or if it dies out. Okay, do you notice a couple of times in there? Hopefully you're seeing all the detail I'm seeing and that the frame rate's fast enough. But I'll show it to you again. I'll play it one more time. But if you watch, you're in hundreds of millivolts, okay, fine. But there's a couple times where it goes a little bit higher than that. You actually get to volts. And I'll pick out those highlights here in a second. Notice you're also in this time seeing California light up, which is interesting. It's one of the first times I've ever seen that. Do you see that band of conductivity on the East Coast now that we've gotten more of this grid filled in? Yeah. And for those of you who are wondering, what the hell is this? This is looking at the bedrock, because I talked about this back in the E3 class. There were, done by the USGS, Jeff Love and crew, did assays and literally took cores of the Earth's bedrock, and actually went in and took a look at what the conductivity is, what the constituent is, did magnetotelluric surveys to be able to get an idea, and then they put all that in the model. And as you can see, there's still stuff that needs to be filled in. It's not done yet. This assay is still going on, and they're also doing Canada as well. So all of this is eventually going to expand out. But they then put all this information into the model that then looks at the magnetic field changes, gets electric field changes from that, and what would be the currents induced in the rock, but then looks at the conductivity of the rock to be able to understand what the currents would be. Right? So then that's why you see the differences, why you see certain areas that have higher levels of voltage and being induced into the rock, into the sorry, I'm being distracted, higher levels of voltage in the actual, in local areas. It's because the rock itself is different there. You actually can drive more currents in certain rock than in other rock. Okay, so as I play it one more time, you can see this. You can see that there's a huge amount of change in here, right? Because there's some strong susceptibility. You can see some susceptibility in here too. And you can see there's a band that goes up in here. And who knows what this is going to reveal. It'll be very interesting to see what the results are when they finally get through Texas. And if you recall last time, we also talked about how the West Coast has a certain, there's a certain part of the grid that's connected to the Texas grid that's connected to the East Coast grid. And there's three main grids in the United States, and this one is very, very isolated. It's only a couple lines that connect it to both the East and the West Coast. So that is definitely a susceptibility, and it'll be very interesting to see what the geology is of this region because of what the implications might mean. But if I don't want to do that. Yeah, there we go. But if I pull up now a couple of the highlights from that movie, during part of this storm, look at this, 1.3 volts. Do you think that got my attention? Now, it's not 8 volts, right? And remember, this is kind of averaged. It's not 8 volts. But, I mean, you're talking, I think this is average, maybe it's the peak. But you're talking, you're well in the red here, okay? So you're seeing a huge type of thing going on. And you're seeing currents up in here as well. Here's that one peak. Look at this, 2 volts. So during this period, and I have yet to go back to actually take a look and see at this time, at 1740 UTC, where the auroral oval was. I kind of want to know, because why would it light up here? I think that's because the whole region that makes it susceptible moved, right? Because as the Earth rotates, actually as the Earth rotates this way, as the Earth rotates, the auroral oval moves, right? And the local times are very different. I mean, different things happen during different local times, and the magnetic field will wiggle and shake differently depending upon what local time you're at. So it's going to wiggle and shake very differently at midnight than it does at noon, okay, or at dawn and dusk, okay. And so I want to kind of check that out, because I haven't checked that out to see really what was going on, why the magnetic field was changing so much there and causing so much stress on the grids here. But notice if I go back again, is it sustained? Kinda. But there's breaks, right? It's not too bad. There gets to be a point at which it's bad, but it's not overwhelming. But this is a G3 level storm, okay? It had my attention. Let me put it that way. Do you think the grids were feeling it? Yeah, they were feeling it. Were they feeling it as bad as 1989? No. But this stuff matters. So here's an example, here's a comparison. 1989, 2003, just a week or so ago, okay? Notice again, the dead zone is because we had less of the assays finished when that reanalysis was done compared to now. So this is always, you're literally looking at from an operational point of view. So for any of you who think that space weather should be done with and excellent and just as good as terrestrial weather, realize that even in the operational arena, you're looking at works in progress. This, if nothing else, should show you how recent this work is, right? These are not well-established models that have been around forever. We're still building them as we use them. The need is so great that we have to use them before we've even built them completely, okay? That tells you how cutting edge space weather is, and how much we're in the process of learning, and why scientists, we don't have all the answers yet. A lot of us are still floating in from academia, just beginning to get into the operations, because we're realizing, oh my goodness, there's a big need. There's a need for us in operations, okay? This is why people like Jeff Love are people who need love, They literally need love from the community. They don't need to be hounded and told that they're bad people because they work at a government institution. Jeff Love busts his butt to make sure magnetometers are functioning at the USGS. I mean, these guys, it's a labor of love for them because they're not well funded. They're not funded like they should be funded, and yet they provide such an insanely important service. And I'm hoping we can change that here soon, because they need more love, especially in the space weather area. Because as you can see, especially as solar cycle 25 ramps up, we're beginning to see storms that I'm not saying are comparable, but are worthy to be put on the same page as that, right? It's illustrative. It's to demonstrate what we're dealing with, right? You're not seeing just a sea of blue. These storms happen more often than you think. It's just that we're getting smarter at how we work our grids so that things don't fail and collapse nearly like we used to. And there's another one. There's the other for the California side. Okay, I mean, look here, here. Had these levels been sustained for 30 hours, could we have had a lot more problems? Yes, I do believe so. But then again, and here's that, I go back one. Had this been sustained for 30 hours, could we have had issues? Possibly, yes. But then again, if it had been sustained, we probably wouldn't have been sitting at a G3. We'd be sitting at a G4 or G5. Okay. Being sustained matters. So it's not just the intensity of the event, it's how long does it last, right? This is why when you see me talk about solar storms that hit and the orientation of that magnetic field is such that there's going to be southward field throughout the entire storm, I go, uh-oh, this could be big. You know, I say, whoa, this is not only going to drive aurora deep down into mid-latitudes, that's when I start worrying about stuff like this. Guess what? That's what this storm was. During a very large portion of the storm, southward field sustained. And you will see me, even when I tweet on social media, right, or I post something on social media, I will say sustained fields, sustained southward field. Look for that word. It means something. Okay. I showed you this. Another reason why sustained matters is because, again, we talked about how this intensity, the peak of it, landed here, okay, over the ocean, not over the United States, for example, or over land. If you have something that is sustained, well, you can have, here's again that electrojet, and then you can see that the bubble of magnetic field changing. Play it again. If you have something sustained, then even if it does peak over the ocean, like here, it will then rotate. Okay? You can see this thing kind of rocking and rolling, right? Local time matters. Here's local time. Local time matters. And so changes in magnetic field over time, fluctuations, how much it's swinging, right, makes a big difference. But also, how long is it swinging? Those are the recipes that you have, that you need to have big sustained storms. Just saying that we have a G3 or a G5 storm, I could go, oh, okay, whatever. If it lasts for 6 hours, I don't care. Now, there's an exception, and I shouldn't say G5 because I don't think I've ever seen that, but there's an exception when it comes to something slamming on super hard. That could be an exception because that EMP, the sudden storm commencement, could cause issues in of itself because that's that radical change. So you don't go from a quiet to G5 like that. But if you ramp up slowly to a G5 and then ramp back down, would it put a strain on the grid? Sure. But if it didn't last all that long, if it was only 6 hours or 12 hours, maybe. Right? We can ride through that stuff pretty easily. But you're talking a day, 2 days goes by, 3 days goes by. It's those storms that have, as I've said before, it's those storms that have typically multiple CMEs in them, right? Where you get slammed by one and you have to endure that, and that's bad enough. But then you get another one that slams just after that, and you haven't even recovered from the first one. Now you got another set, and you get these composite events, what we in space science call composite events. That can just really make it a nightmare for you. And I mean, incidentally, those composite events cause problems with stealth CMEs as well. Not nearly to the level of this, but it's another kind of forecasting extreme because you've got these invisible, really wispy CMEs that by themselves don't mean anything, but sometimes they're embedded in fast wind streams. And when you have these big fast wind streams, or they're embedded, in front of it or something, being pushed behind by these fast wind streams, so they're embedded in something called a stream interaction region. And stream interaction regions in fast wind by itself can cause a solar storm to happen at Earth. But now you add the stealth CME that you didn't even know lifted off because it's invisible. You add that to the mix, and now you'll get a G2. And it's like, whoa, where'd that come from? And we call those problem geomagnetic storms because, if you have astronauts out doing an EVA because they don't think there's anything going on, and suddenly you get hit by one of these things, and you're sitting at a G2 level, whoa, that can't happen. That can be extremely dangerous. And so as we start having more activities like Artemis, for example, where we have people out on the moon doing this stuff, you don't want this kind of thing going on. There's all sorts of complications that you have to worry about. At any rate, so to make these types of storms be grid inducing, it's the composite events. It's the ones that add together. It's the ones that come back to back to back. Or, in the case of the stealth CMEs, it's the embedded ones. These composite events can be the ones that really cause issues. And sure enough, when you look back at the biggest, the most extreme of the extreme in history, that's what you end up seeing. It's typically something that is not just one event, but several. Now, in this one G3 that we just had, we had a CME, and then we had some fast solar wind afterwards, which kind of made it linger. Did it help become a G3? Yeah, I don't know, but it helped sustain the impacts over time, which is why we had Aurora. We've had Aurora since, basically the turn of the month. It's finally just calmed down over this last week. I mean, but we had like a week long of some insane Aurora, some beautiful Aurora that came way down south. I mean, we saw it in Brittany, France. We saw it over the Swiss Alps. We saw it in Death Valley, California. I mean, it came pretty far south. And again, it wasn't just the CME acting alone. We had the fast wind along with it. But nonetheless, it's still not it still wasn't like two big CMEs coming in. However, all of that conspired still to have some very interesting effects that go beyond GICs, right? So GICs obviously and impacts on the grid are one of the big things, sure, but not the only thing. So for instance, one of the things that Chris Mason was sweet enough to do, and so was Vince Ledvina, who actually pointed me out to this. Vince, I think, texted me, I forget, one of my students who's Vince Ledvina. Some of you might know him as Appalaps from an astrophotography on YouTube, but he also now is a full-blown space physicist. He's in Alaska Fairbanks, learning all about Aurora from an ionospheric physics point of view. And he's also one of my students from Millersville. And he's also worked with Erica Palmerio. I mean, he's worked down at Predictive Science. He's now taking an internship at Aerospace. The guy's everywhere. But he pointed me to Chris Mason's post on Facebook that had to do with oil rigs. And I was stunned because he said he had worked on the well sites for 30 years and had never seen a time where they had to actually shut down rigs. And that tells me that likely that's because we're in a stronger we're in a stronger solar cycle than we've been. I don't even remember from the last solar cycle ever seeing a G4. I think we had maybe one or two G3s, but from the last solar maximum, man, we didn't really have much. But we've already had a G3 here, right? We've already had we've had two G3s. As a matter of fact, the one in November of a year or two ago, where we saw Aurora clear down to, where was it? Joshua Tree, California. That one really could have been a G4. It just didn't last long enough, but I think it was definitely going there. As a matter of fact, I should go. I did look at the HP indices, which are like KP but shorter, and they were at G4 level, so KP of 8. And so we're seeing these stronger storms now. And Chris had posted this oil rig thing. What happened in this case is that when the Earth's magnetic field is rocking and rolling, right, the precision magnetometers that they use to get position location to kind of know, because it's like their compass, right? They have to use that down in the rock to really know where they're drilling. And there was so much noise, so much change in the field that they couldn't. The azimuth in their pointer went haywire, and they just couldn't make sense of it. So they literally had to stop drilling several times. And apparently, and this was in Saskatchewan, there's apparently another rig. This is by way of stock picture. I don't think this is the rig he was on. But there was he said he got reports from other people in Saskatchewan or neighboring rigs that had similar problems. And does this happen every time? No, you have to be at the right place at the right time. The storm has to intensify at the right time. But just seeing the aurora near the rig kind of tells you that if your aurora oval is right near your rig, you're probably dealing with some very intense magnetic field changes and very quick changes. It's not just a slow change, especially at high latitudes. Neat thing is that it got picked up by space.com. That was really cool. And at the same time, during this G3, Elon Musk and SpaceX, they decided to delay launch. What launch was it? I forget what number it is. But they paused for a few hours launching their new Starlink payload. And when they did launch, I remember saying, please launch over 400 kilometers. I was like, please get up there, get up, because they're used to launching at 210. They raised it up to about 300, a little over 300 after their February, the launch of the classic launch where they lost like 40 satellites. Remember that? Which we knew was going to happen. I mean, I even told Vince when he was a student that this is going to happen. It's just a matter of time, not if, but when. Sure enough. So Elon's lost 40 and then another 6 a little while ago during another big storm. But he raised up the orbit insertion to 300 something recently, after that, the loss of 40. And then when things got quiet, he lowered it back down. And I got that straight out of one of the scientists that runs the WAM IPE model at SWPC. I heard her talking during the AMS conference this year. And she said, he's already lowered it back down to 210. I went, well, yeah, okay, that's their trade space. So I actually posted something on Twitter saying, please, 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 you're going to delay. Well, that's fine. Delay is one thing. That's great. That's wonderful. But please launch higher. Don't launch it at 210. Please raise your orbit to 400, 400 kilometers. I'm like, thinking, okay, that's still low, but it's safer, much safer than 210. I mean, they'll lose it really quickly. Well, it turned out they did launch 375. 370, 375, something like that. I didn't quite get my 400, but at least they were smart. They raised it up higher than they had ever raised it. They didn't launch back into the 300 something, the low 300s, which is where they had raised it before. With this G3, they raised it up to 375, almost 4. So I feel that was a victory because I got him to, I didn't, obviously. They who knows where they got all their information, but it makes me feel good that space weather is part of the trade space. And I even wrote that in the tweet I put up. I said, thank goodness space weather's finally made the trade space when it comes to launching Starlink. Because that's a big deal. There's a lot of things in that trade space that they have to look at that cost money. And sometimes launching at lower altitude and losing a few more spacecraft is actually a better solution than making sure they're all space weather safe. Because there's so many other things that contribute. But at least for a little while, it's getting better that SpaceX is paying more attention to space weather events. And so space.com picked it up. It was great. So we have both oil rigs and Starlink being affected by space weather. I think it's really cool. I think it's wonderful. It's not just about geomagnetically induced currents, right? And we're going to start seeing more and more of this. This is becoming a bigger and bigger player, I think, on the main stage. And as you can see, it's like weather, guys, right? How different is it than weather, right? They have to stop their production or stop their drilling for a short while Just like you have a delay of game at a baseball game because of the rain, right? Same thing here, had to delay their launch. Not because of a big radiation storm or that kind of stuff, but because of a geomagnetic storm and the thermal expansion you get in the upper atmosphere during a big solar storm. Isn't it cool? It's like weather, you know, it's a mild inconvenience, which is what I've been saying for years. Space weather is not catastrophic or nothing. It's not either a sunny day in space and everything's quiet and fine, or it's Armageddon. It's not that light switch that everybody has been taught by Hollywood and everyone else to think space weather is. Space weather is just like terrestrial weather. It's just a little further up, right? It causes mild inconveniences. It causes delay of game. But we can work around it. We can work through this stuff. Look at it as weather, right? Just another aspect of weather. It's just the invisible side of weather. But it's still just weather. So to emphasize my point, GICs can affect more than power grids, right? Railroad tracks. Hey, we don't got, well, we got some trains that look like that. We also have trains that look like this. How about in Japan, right? Bullet trains, passenger trains. Believe it or not, actually, I should have put that here because I'll show you. Where is it? There was. I'll get to it. Japanese trains. I should have probably waited for that. But I'm going to show you the history. Believe it or not, it may seem like sci-fi, but believe it or not, we have had big impacts. Now, you might recognize this term, the Great Railroad Storm of 1921. The reason why you might recognize it is if I go back to, where is it? Here. Okay. So here's the March 13th. DST was minus 650. DST for the 1921 Great Railway Storm was minus 700. So bigger than the Quebec storm. Some people called this a Carrington class. Don't know, but dang big. I think it's probably just a superstorm, but the reason why people thought it was a Carrington class was because the effects were so intense. Okay. But nonetheless, it's an historical storm and has implications today. Currents don't just run through rock and up into transmission lines. Railway lines are better than rock. They're metal, right? So we had a Great Railroad Storm of 1921. And as you can see, here are some newspaper clippings. Go to, and I might get, I don't think I'll get in trouble for this. Spaceweatherlive.com has these clippings up. So does solarstorms.org. I love solarstorms.org because they've got all of these just back to back to back to back to back with lots of clippings for just a veritable buttload, pardon my language, of solar storms over the course of time. And it's really interesting to look at these. And then there was a paper done that actually is talking about this actual sunspot cluster. This is the bad actor that then launched solar storms that caused the Great Railway Storm. And yeah, I mean, look at this. I love this. Aurora not visible, its absence being contributed to atmospheric conditions. You mean like it's cloudy? This is like the LinkedIn version of reporting, it's just cloudy, guys. It's a much, much cooler way of saying. And I'm just showing you the paper where this is come. Again, this is from spaceweatherlive.com. They have nice. I grabbed it simply because it had this sunspot number, or some sunspot view. I have not read this paper. My apologies to the authors, but I did want to put your paper up so that you knew where the source of this came from. And here's more studies of this particular event by Mike Hapgood, which is, Mike is one of the chief scientists, if not the chief scientist at the Met Office UK, the MOSWAC, very, very savvy scientist, and is very much into operations, and was one of these people, once again, who's moving the needle forward in the UK regarding trying to understand historically some of these solar storms, so that we can get a better idea of what, of how these geomagnetically induced currents can cause problems, and how to quantify them, and how to quantify the the fact that the magnetic perturbations are things that we need to look at as the first derivative, as the changes, quick changes over time, and not just what the total number is. So I'm quite appreciative. Jeff Love, again, USGS. You can imagine that's why he's coming up with this kind of thing, because again, GICs are extremely important to these people. These are the scientists that are leading that, along with Antti Polkanen. These are some of the scientists that are on the front end of this, and really that the 1921 railway storm. One of the reasons why it was such a big deal was not only did the GICs jump the lines and get into the railroad tracks and then cause all sorts of issues for the railroads, but then they also got in because of the railroad stations were connected. There was actually telegraph lines that were connected to the same system, and the telegraph systems ended up getting electrified and then caused buildings to catch on fire because the telegraph wires went off, caught paper on fire, caught the curtains or whatever things on fire, and then the building burned down. And that happened in multiple places, and it was all around railway stations. So it didn't, in this case, it wasn't the telegraph wires that did this, but it was hundreds and hundreds and hundreds of miles of unbroken lines. Now, unlike power stations where you can take lines and terminate them, and put break points. Can't really do that with railway, can you? Right? Because you got to get from place to place. You can't break them like that so easily. So this is why this is becoming a bigger deal, right? Because especially as we get more and more rails up, and obviously Japanese are the leaders when it comes to railway, and they have all the special kinds of railways that are either moving very, very quickly or running on on current systems that are very, very different than what we're used to. And so I've scanned this paper, but I have not read the whole thing all the way through in depth. Right, I've scanned it enough to know that it's a very interesting study, because they've done a comprehensive view of all their railway stations or railway lines throughout the region, and they've actually looked at the GICs and the values that they're seeing at the substations in their network. So what it's going to probably do is get them to start looking at how power grids break things up and slow down, stop these GICs from really adding up. Because remember, they're integrated, right? Little bit by little bit, by little bit adds up if things are unbroken over hundreds and hundreds of miles. Well, that's what they're seeing here. So they're going to have to try to figure out how to fix this. Okay. So it's very, very interesting that these things are becoming more and more common. See this paper date? 2021. Cutting edge research. Okay. People are waking up to the fact that space weather can be, that's it. People are waking up to the fact that space weather is critical to what we do. And you know what, just for grins, I will show you. If I have it up, let me move this without, oh poop, where are you? There we are. Yeah. So this is the 1989 storm with the power grids. And I'll let you see. So you can see the time. So this is all the grid, all the electrical lines. And they've gotten all of the assays underneath. So as you can see, you'll see when the storm actually hits, you'll see how much things light up. Okay. And I did show this last time, but I wanted to make sure that I showed it again, just because it's very interesting. Whoa, did you see that big sudden storm commencement? You'll notice how things light up from kind of the top down. And you'll see things that are like waves that kind of move across, either from this way, or from top to bottom, and then back up again. So you can see just in the power grids themselves where the springs were that were taking the heavy loads. And when you take some of those springs out, now the other springs in the vicinity have to carry more, right? And have to have a higher demand for reactive power. So then those had to be, take the load. And then those couldn't handle it. And those would fuse or be taken offline. And slowly but surely, you end up having the entire grid collapsing because of this. Okay. We're not even talking about Canadian. This is just in America. Pretty cool. Hi, Art. Good to see you. So this is, and does anyone want to see the magnetic field? I can show you the magnetic field doing the Austin Powers thing. So you can see what the swing dance, the marathon swing dance looks like. Anybody want to see that? Because I'll show that. Is that 1-to-1 scale? Not sure what you mean. The volts going from 0.01, realize that this is a logarithmic scale. 0.01 times by 10 is 0.1, and then times by 10 is 1. So this is a logarithmic scale. So there's a big power swing in there, okay, or a big voltage swing. So yes, you guys want to see it, okay? Through ground conductivity. Well, I don't know if it's going to be quite high enough resolution for you. As a matter of fact, I'll just show you so that you can see really quick. Here are the assays, at least at that time, and I'll play this for you just for fun, just really quickly. So these are where all the assay points were actually done. So ding, 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 ding. So it's not really at high enough resolution for you to be able to find groundwater, but as you can see, so this is not with a grid powers anymore. This is just what the assay, what the model inputs showing the assays that were made, what that covers, and so you can actually see how it lights up a lot more. See that? So there's a lot of working parts to models like this, because the working parts require that you understand the ground conductivity. The working parts require that you understand the latitude dependence. The working parts require that you understand the timing of the impact and the sustainability of the impact, and not just the strength, but how much wiggle is going on. And then it requires, what are the lines like? How long are the lines? What direction are the lines moving? Or have they been set up? Are they lines going from north to south? They're going from east to west? All of that factors in. Okay, so these problems are very complicated. And we do not have a complete handle on it yet, obviously. Okay, so here's the Austin Powers. Okay, so what you're going to be looking at now, and I'll explain this. This is the work that Cameron Gonteski did for, believe it or not, for the Space Weather Trek database. And I asked her, I said, hey, can you give me your frames? She said, sure. I said, I'll make a movie. She's like, cool. So I've used this movie ever since. And Cameron now is, again, a ex-student of mine. She now works for the airlines as a space weather expert. Yeah, and I'm very proud of her. And okay, so what you're looking at now, if you notice it's kind of curved, right? So you're, in a sense, kind of looking at the spherical L shells, right? Not spherical, but you're looking at the foot points of these L shells as they come in lower and lower and lower, right? So super high L shells, super low L shells. Well, super low L shells down here, right? So you're talking about the auroral zone, L shells that are out at L6 or more. Here you're talking about L shells that are, a bit lower, mid-latitudes, where KP and all that kind of stuff. And then down here would be ring current stuff, okay? But you're still getting an idea of what the magnetic field is going to be doing. So what you're looking at are vectors, or these are little arrowheads. And the arrowheads will get longer. You actually see actual arrows coming out. They'll get longer as the strength of the field changes, right? So as the field gets stronger, you're going to see not just a color going from black to purple to white, but you're actually going to see the length of that vector. You're also going to see a direction, so the vector is going to swing. So that's why I'm saying you're going to see Austin Powers doing like this kind of thing, okay? Because you will very soon. So this is the swing dance, the marathon swing dance that I'm going to talk about. And as you can see, the vectors, the little arrows are teeny tiny down here, and already they're a little bit bigger here. Why? Higher latitudes, higher L shells. There's going to be more magnetic field changes here than there are here. But watch how they wiggle and watch how they go, you know, big changes kind of propagate down and then things go back up. But you'll see how incredibly busy it gets. And remember, magnetic field changes over time is what induces the currents into the ground. Okay? So it's not not with the vectors, these little arrowheads staying still. That doesn't cause change. When they move and when they strengthen and weaken, those changes are what matter. That's why we have to look at changes over time instead of just the values themselves. So here you go. See, it's all happening up at high latitudes early on. Hardly anything going on down here, right? But that's going to change here pretty quick. And trust me, you'll be able to tell. Oh, getting a little bit, right? It's coming. Here they go. It really is beginning. It's going to kick in here soon. There we go. Boom. Look at this. Whoa. This is Austin Powers going groovy, baby. Look at that. Look at, even clear down here. Do you see? And it's all wiggling. All these different directions, back and forth, back and forth. And we're talking about the vector, what's called the horizontal component. This is the component that is just literally in the same plane of the page as the ground, parallel to the ground. So it's just kind of wiggling just all the way around. Right? So it's the sustained marathon swing dance that makes the difference. However long it can stay sustained. And you see it working from high latitudes to lower latitudes when the big stuff hits. Yeah, here's the last little bit of it. But notice that Canada just gets it hardcore, and then the United States is, I always call the United States kind of like the Goldilocks zone, because it doesn't get the nasty stuff that Canada gets, but it also doesn't get the EMP that the lower latitudes get, like Australia gets. It's kind of in this you know, not too hot, not too cold kind of zone. So I do call it the Goldilocks zone for space weather. But anyway, so hopefully that gives you some feel for not just the 1989 event, but which we call our standard candle, but also, you know, the recent event that we had in just a week or so ago. Is that good? And that's it, guys. That's all I have. That's all I have for you. We have finally, whoop, what am I doing? Didn't mean to do that. We have finally completed our ground level courses. So I'll pop this like this just in case. Look at all these slides. Gone through a lot. Okay, has any of the work been done in Canada? Yes, it does. It does not stop at the border. There's, like I've mentioned, and this is Kim's question. I saw at the AMS just this year, the experimental version actually has it going up into the Canadian provinces. And it doesn't, I don't remember how high it goes up, but it goes up easily past a lot of the big cities before you get into the north, the territories even further upstairs. So it's going to get all of the big cities, and I do think SWPC is going to take that into account and have it actually as part of the SWPC consortium. And I don't know if it's just the USGS. I think they're partnering with Canadian Geological Survey government agencies up there. I don't know the details of that, but yeah, that is coming. So just be aware. And it's important because a lot of the American utility companies and the consortiums, we actually couple into the Canadian grids as well. So we need to have all of that. We need to have an understanding. It's not just because we've got a border, a country border, doesn't mean our electrical systems care. They're all connected. So it's important for us down here we have Canada's best interests at heart because it matters to our grids down here, and vice versa. It matters with Canada that American grids are healthy as well. So we're all in it together. You know, solar storms don't care what latitude you're at. I mean, they do, but they don't care where your country's latitude stops. Let's see. So the composition of Earth crust is a factor in the propagation of telluric currents. Yes, exactly. So that map impacts the electrical grid for the U.S. is the one that Canada would have been more spectacular. Yes, it would have been more spectacular. Yes. But in certain areas, because remember, it has to do with conductivity of the ground too. So when I put this one up here, for example, which is the one, there it is. So when I put this one up, for example, all of this extends into this area. So this whole area, and in Quebec, that's why the Quebec grid went down. The Hydro-Quebec grid went down. It's because it's got magneto, the telluric currents are pretty intense, and it's got the conductivity that would require that couples into that causes that. So that there was a bigger GICs being coupled into and sustained longer than you have it if you don't have very high conductivity in your rock. Okay. More feed us. No, can't you tell my voice is my voice is fried? That's about when I know. It's almost 3.5 hours, guys. So we're we've got to cut it off here. Thank you, Mike. I appreciate that. And Mike Richardson, you say should have been able to see it in 1989 if it was clear. I saw it in Louisiana. Yeah, Mike Richardson, by the way, he saw aurora clear down in Louisiana in 1989. He was talking about how the police actually thought it was a fire. He had to actually inform the police that no, it wasn't. So Mike is a really good person to chat with if you want firsthand experience of what that storm was like. Clear down in here, clear down at the base of the United States. Pretty amazing. Thanks, Mike. I appreciate you reminding us about that. I wanted to. That was a good thing to highlight. Yeah, he's got really cool pictures of it too. So this is ground conductivity modeling, not necessarily modeling of the electrical grid lines themselves in the effect of conductivity. We did. This is showing the electric field, but when I showed you the electrical conductivity, they actually were factoring in grid lines or grid electrical lines. The biggest issue that you have with that is that a lot of the power grid folks, the utility companies, they don't want you in there. They're like, no, this is proprietary. We ain't letting you in. You can't measure. You can't put equipment on our property. No way. So there are some issues with that. And I don't know all the ins and outs as to why. I do remember talking to some people at National Grids where they were, this is in the UK, they were definitely not letting anybody put any type of equipment, whether it was science grade or academic based or not. And that, that happens with satellites too. There's a lot of satellite vendors that go, no, we're not going to tell you what happened to the satellite. Yeah, we can tell you we had a space weather anomaly, but we're not going to tell you what happened. And the reason why is because they don't want, that's their secret sauce, and they don't want anybody to know where their vulnerabilities are, and they don't want people to maybe reverse engineer the materials or the techniques or what it is, the equipment that they're using. So, that's always going to be a problem when it comes to industry, is getting them to open up, even in an anonymous sense, to let us understand it as scientists. And I don't think there's a quick and dirty solution to that. That's just negotiation. And that's something that a lot of these operational scientists have come across many times. I know Jeff Love has talked about it multiple times. Janet Green, in terms of satellites, Paul O'Brien, Joe Mazer, the list goes on. Joe Fennell, have all talked about this kind of thing. It's even a bigger deal with spacecraft than it is even with grids, but it's a big deal there too. So hopefully that helped answer that question. A lot of people miss aurora because they're sleeping. That's very true. Yeah, like the big storm we had back in November of about a year or so ago. It was 2 or 3 in the morning when it was just unbelievably dazzling, and they were getting coronas. They'd gotten coronas in North Dakota, and coronas had been moving down to South Dakota at that time, and people in North Dakota were going, oh my gosh, we're inside the auroral oval. This is nuts. But it was like 3 in the morning at that time. So there are very few people were actually awake to see it. Long duration learning. Yeah, no kidding. I agree. Okay, the Met Office in the UK provides space weather info. Right, exactly. The MOSWAC, the Met Office Space Operations Center. And I've actually been there. And I know a lot of the people that work there, including Mike Hapgood. And they're fantastic people. And they've actually helped SWPC. It's a really good handshake. The neat thing is that the UK is, their ground, especially their national grids, their ground conductivity is a bit different. They're also different. They're not at the same magnetic latitude as we are here. We are at lower magnetic latitude. They are a little bit more insulated than we are because of the fact that the auroral oval tilts down essentially over the Canadian and the United States. It tilts away from the UK, which is why the UK doesn't get as much aurora as we do. That's changing a little bit as our magnetic field shifts and the poles are shifting more towards Siberia. The magnetic poles are shifting more towards Siberia, but it's slow. It's slow. But you know, there's a lot more people out there looking for aurora now, and cameras are a lot more sensitive. So that's why we're able to see it a lot more. I mean, we're picking them up on webcams, for goodness sake, right? There was two webcams, a webcam in France and a webcam in the Swiss Alps that saw aurora just this past week, which was just really cool. I just find it fantastic. Oh, did you, Chuck? You saw aurora in 1989 from the cockpit of a 737 over South Carolina. Yes. Wow. That is so cool. I hope that didn't scare the you-know-what out of you. There's fire in the sky. I wonder if you recognized what it was when you saw it. I would have been taken aback, that's for sure. That's a great story. Thank you for sharing that. So having the ancient Creighton granite is more conductive than sedimentary. I don't know. I am not a geologist, so you would have to talk to a geologist more. That is totally outside of my expertise. I am not a rock person. Just wait till the Earth flips. Well, remember, Ronald, the magnetic field of Earth, it's not the whole magnetic field. It's only the dipole component of the Earth's magnetic field that's flipping. We still have the quadrupole, the octupole components, and then higher harmonics. All of those will remain. So likely we're not even going to have two poles. Eventually we're going to have multipoles. And we're actually beginning to see some of that already, because if you go down to like the South Atlantic anomaly and some of the other ionospheric anomalies that we have that are magnetic in nature, people are beginning to see aurora from them, which is really cool, because the magnetic field is weakening, the dipole component is weakening. And so that's really where you're seeing a lot of the changes thus far. If you're Hawaii or in Chile, for example, and you take a really good camera and you face it toward the South Atlantic anomaly, for example, you can, in Hawaii, that means due south, you can actually see something that looks like a striated air glow from big geomagnetic storms. That is equatorial aurora from these anomalies, and there's papers on it. And it's really cool because it's beginning to pick up, because the SAA is beginning to change. But don't worry, it's not that the Earth's field is collapsing or anything like that. It's just the dipole component, and as it flips, it's going to expose the quadrupole component that has 4 poles, and the octupole component, which has 8 poles. So we're going to become a multipolar Earth for a short while. Okay. Don't worry, the sun does it every 11 years. We've seen it many times. Nothing bad. It's just going to be really crazy space weather for the period of time that it happens. Sadly, we're probably all going to die long before the pole flip. It just is what it is. We're going to see lots of cool stuff and changes, but it's going to be just incremental. The biggest thing that I have, my biggest concern about the pole flip is really, what are the space assets going to do? What's going to happen, because our radiation belts are going to do what? I don't know. Maybe we won't have radiation belts for the period of time that the dipole field component of our field flips. I don't know. And I'm not sure a lot of money is being put into that yet for modelers and stuff, for people to do a lot of research in that area. But that will also be changing soon, right? Because as it becomes a bigger thing to talk about, more people ask questions, it becomes an interesting research concept. People are needing to plan for the future, and how do we deal with this? What do we design satellites for? All of this stuff. And people start recognizing, oh, maybe that's money we need to, that's an area of research that we need to put funding into. So that will slowly change. But I don't think we're going to see as much of that and see all the answers we want for quite some time yet. But it's a very interesting. Tamitha, can you give us a shout out to Scott McIntosh? Well, of course. Scott's a good friend of mine. I talk to him all the time. It was he and I on that polar vortex thing. I showed Scott the polar vortex, and because it's something that we're looking for similarities between the sun and the big gas giants, because there's something going on special around 55 degrees latitude. There really is. There's something to do with how the sun's dynamo is made, and that's not accurately captured in any of the dynamo models. So Scott's empirical model, Scott McIntosh and Bob Lehman and the NCAR crew, UCAR crew, they're doing some revolutionary empirical modeling of the sun's magnetic dynamo and solar cycle activity. And it's really cool what they're revealing, because they're revealing what we have yet to do, where the holes are in our in our understanding. And that makes them, sadly, it makes them target number one. I mean, they've got a lot of arrows in their back, but I really commend them because they're willing to stand up for what they believe in. And a lot of their beliefs are turning out to be true. So it's cool. It's fun. It's fun getting into a field where, there's a lot of scientific discourse and arguments and stuff, but also true movement forward. It's a fun field to be in. Okay. You're going to take your multimeter outside to measure rocks. Well, you're going to have to dig a really deep hole. I'm not sure it's going to work quite that way. Cute though. Okay. Let's see. Oh, and Smash, you actually did bring up a good point. When those assays were being done, I did ask Jeff Love a few years ago. I said, did you guys omit times of geomagnetic storms when you were doing your telluric assays? No, they couldn't. They hardly had the fund. They barely have enough funding to get it done, let alone to do it wait for times that it's quiet. So they just did it when things were scheduled, and if there was a geomagnetic storm, they did the best they could. So does that add error? Sure, yeah, it does, and he knows it. But that's you got to start somewhere. So just be aware of that. These maps aren't perfect, right? But it's a start, and it gives us a direction how to improve. So okay. How does magnetic poles shifting affect HF propagation? Well, very easily. Imagine you've got, the auroral oval, for example, right? And you get auroral propagation in those regions. Well, if that auroral oval is shifting, right, or eventually even possibly becoming multipoles, well, you're going to have those same kinds of effects that you get in the auroral region. You're going to have them in other places, right? So could that facilitate radio propagation in certain arenas? Yes, sure. Could it create other things where you could possibly, as a magnetic shield weakens, for instance, when you have radiation storms, depending upon the strength of the radiation storm, you could actually create sporadic E layers. There's all sorts of things that can be created. You would get that not just happening at the poles, but happening anywhere around, at these lower latitude areas where we have these magnetic anomalies. So it all depends. And then things like the equatorial anomaly. Boy, that's crazy. These are really good questions. Because as the equatorial anomaly, which are two bands of higher electron content that are both in the magnetic north, just about 10 degrees north of the equator and south of the equator, that oftentimes cause problems for radio propagation. For example, if you're inside the equatorial anomaly or outside of the equatorial anomaly, you may have problems communicating between. Which is really sad for some de-expeditions that have gone in the past, and where they go is like into some location that's right in that equatorial anomaly, and then they get nothing and nobody contacts them, or they hear everybody but they can't contact them back. There's all sorts of weird scintillation that occurs in that region. But that equatorial anomaly is based on the dipole component of our magnetic field, because it has to do with the fountain effect, and I won't go into the details of that right at the moment. But that, of course, will change dramatically if the dipole field disappears, and then you have the quadrupole field. You're going to have localized equatorial anomalies likely that won't be global anymore, or will be global, but then they'll be weird. And the way I can look at it is just the way I talk about the sun during solar maximum. I mean, it's magnetically, it's like a lava lamp. You have these magnetic islands. And so we may have to look at how the sun, look at what the sun's magnetic field looks like to kind of get an idea of, okay, how do we deal with radio propagation in these types of situations? Incidentally, we'll be facing the same kind of thing if we try to do skywave on Mars, because Mars doesn't have a dipole field. It has a remnant field from a dipole field that existed ages ago. Now it's just remnant in the rock. And radio propagation is possible at Mars. It takes different frequencies, but it's also going to have a totally different behavior than it does here at Earth, because you don't have a magnetic field that is the same shape as what we have here. So we're going to be learning a lot about how to basically colonize Mars and do skywave on Mars by these types of things that are occurring with our own magnetic field now. It's kind of neat. It's a really cool time to be alive, to be honest. Oh, Jerry, I'm so glad you're here. Okay, hopefully that answers that question. Yeah, time to rest my voice. I agree. All right, guys, is there any science nerds unite? Yes. Yeah, don't get me excited about some of that stuff. I could talk about that stuff forever. I'm just looking to say, are there any other questions, guys? Currently streaming. Okay, you guys are talking about your channel. That's cool. Right on. Is it possible that the sun's going to be a planet in the future? No, no, not at all. Not at all. I don't think our sun has the ability to go supernova, but it's not going to become a planet. So, VHF and SATCOMs would be good for Mars. Yes, sort of, because the problem is you can have SATCOMs and you can have a constellation of spacecraft, but the problem is Mars's atmosphere goes opaque to radio propagation during radiation storms, during inclement space weather. And the reason why is because these particles can go all the way to the ground. And so they light up the atmosphere like a big D layer, and it makes it really hard to communicate. Now, are there frequencies that could probably get through? I don't know. Only time will tell. But will there be a lot more? Mars is far more susceptible to space weather than Earth is. So we're going to have to learn how to live with space weather here and get better at it here and dealing with the problems here before we go to Mars and expect that everything's going to be easy, because it's likely not. With a much more tenuous atmosphere, Mars has lots of other issues that we don't necessarily have here at Earth. So, okay. All right, guys. Yes, time to rest my voice. Thanks, Jerry. I can tell. Me too. I'm tired. Tired. You're very welcome, Ronald. Thanks for another well-explained course. You're very welcome. Okay, guys. Thanks, Johnny. You said thank you for sharing your knowledge and actually having a conversation with us. Of course, I always have conversations with you guys. I learn so much from you. I learn as much from you as you do from me, I think. So I will always be forever grateful. Okay. Okay, guys. That's it. And hopefully we've finished the whole, sun to mud, at least on the basics of the first chef and the second chef. And you guys have a much better feel for how all of this stuff couples together to give us impacts on the ground. And we'll have to figure out what to do next when it comes to space weather courses, because we might have to take a different direction. All right. So thank you very much, and I will talk to you all soon.